Well, thanks, Andy. I understand that, so I'm really happy to be here. I've wanted to come to this meeting for a long time, and but I understand that perception and vision was actually banned from the meeting, right, until a couple of years ago, explicitly on the website. You cannot apply if you're abstracted. So I'm really glad, right, to be here now. To hear that endorsement is just heartwarming. So I'm going to talk about visually guided locomotion, and my project in life is to try to put together an understanding of the dynamics of action together with perception and vision in particular. So that's what I'm going to try to do today. I want to start with what for me is the big question, which is what is the organization of behavior, right? So we observe order and pattern at multiple scales in human and animal behavior. So a lot of us here are focused at the individual level at motor coordination, kind of intersegmental coordination of the limbs. How do you generate those patterns? There's also coordination between an agent and the environment, which is one of the things I focus on, and the rough terrain problem, right, is a kind of prime example of that. And there's also multi-agent coordination between agents, which is really a problem of collective behavior. And today I'm going to try to focus on these two levels of the problem. Since everybody else is doing so well with that, I have nothing to add. So there's a great temptation to attribute the organization and behavior at all of these levels to some prior structure, right? A controller, an internal model, a CPG, a brain. But I think this just regresses the problem, right? Where did that prior organization come from? And often you kind of push it off onto evolution if you're in psychology or neuroscience. So I think the challenge for science is to understand how order at all of these different scales might emerge for free as a product of self-organization, of some principles of self-organization. So this is the origins problem. Where does the organization and behavior come from? And cognitive science, neuroscience, psychology are particularly vulnerable to the temptation of assuming that there's prior organization or assuming that evolution solved the problem for us. A dissenting voice came from James Gibson, who is long at Cornell and is one of my kind of heroes. And Gibson in 1979 said, control lies not in the brain, but in the animal environment system. Behavior is regular without being regulated. The question is how this can be. Right? So this is one of these Zen koans that Gibson was famous for, where he kind of poses this statement and then leaves it up to us to try to figure out what it means. So for my field, I think many people think they're studying this, okay, but they're really studying this. We're not an isolated brain that's imposing organization on the system. That brain is in a, embodied in a physical biomechanical body. It's embedded in a dynamic, complex world, and all of those constraints are brought to bear on the organization of behavior. So I'm going to argue that biology exploits physical constraints, ecological constraints of the animal's niche, and informational constraints, which is what I'm going to talk most about. And that behavior isn't prescribed by the brain, but rather it emerges as a stable solution of the dynamics of within all of those constraints. And so that's the problem. How do you get there? Well, robotics offered these wonderful extreme cases, okay, which I just have loved following remotely over the last decade. So on the one hand, you have Asimo, this is carrying cold in Newcastle here. You guys know all this stuff. But Asimo has 26 actuators, computationally expensive. It's you create a whole bunch of control problems, and it's inefficient to boot. On the other extreme, there are the passive dynamic walkers generated by people in this room. So this is the Cornell biped of some years ago. It exploits the physics of pendulums. It has just one actuator at each ankle. It's computationally very light, and the cost of transport is close to that of humans. So which way are you going to go, right? If you're evolution, right, evolving a stable, organized walking system, if you exploit, so the message for me from this is if you exploit physics, you can get stable, regular behavior for free, right, out of all of those constraints, and you can greatly simplify the control problem. All right, so everybody knows that in this room, or maybe believed that at one time in this room. We'll hear about that later. So the problem is we now know that these sorts of stable solutions are fragile, they're hard to find, they're hard to initialize, and moreover, for behavior, order isn't the only problem, right? Behavior is also adaptive. So behavior doesn't just have to produce a regular pattern, it has to be adapted to the environment. It's got to vary over time so that action is tailored to the environment. And for that, I'm going to argue we need at least visual, or what Junho called non-blind information, in order to solve that kind of problem. So here are two more robots. Okay, this is kind of from the AI side of robotics, which I think have a kind of analogous take-home message. So on the one hand, in the standard Go-Fi tradition, you have a kind of model-based control where all the robot's sensors are used to construct an internal model of the world. You use that model to do explicit path planning. You generate an action plan, a series of commands or forces that have to be executed, and then you execute that plan. So this is, computationally expensive, but, kind of guarantees you to get through the door in this instance. But on the other extreme, you might have an information or a computational light solution, which I think of as information-based control, where everything is done online. The behavior is emergent. So you're using, say, optic flow to steer toward your target. You use the shift in optic flow from your target to regulate the balance of forces, and you just keep doing that, and you end up tracing out a path that emerges online, and there's no planning involved. There's no internal model involved. It's very computationally inexpensive. So, my moral from these pair of robots is that if we can exploit information in the same way we can exploit the physics, then you can also simplify the control problem. And in particular, I'm going to suggest that biology combines these two things, right, by using information of this sort to tweak the dynamics of an organized system. John Mathis gave us a really nice example of this yesterday in his poster, which is this problem of foot placement on rough terrain, which I worked on my postdoc with David Lee many years ago for running. And the point is that a lot of people here are working on these sort of reactive reflexes. So what if you put your foot in the wrong place? Can you recover based on a compliant limb? But it might actually be more economical to have anticipatory adjustments based on prior information about the upcoming terrain. And so that's what John is looking at. And basically, to sum up a whole bunch of elegant experiments, basically people need to see the target that they're going to land on during step n-1, okay, in order to initialize the dynamics of step n to take maximum advantage of the dynamics to get on the target. And so in this case, you're using visual information to tweak the initial conditions of that step n to maximally exploit the dynamics. And so you're using a lot of sensors and control, but you're doing it in the interest of minimizing the adjustments that you need to make to the step cycle. And that, of course, is also energetically efficient. So this is my attempt to try to analyze that combined system, right? How you're going to integrate information together with dynamics. And so behavioral dynamics is an attempt to try to analyze the interaction between an agent and an environment while you're doing something like walking, okay, through the world, or something more complicated. So I'm going to try to summarize that here. We're going to treat the agent and the environment as a pair of coupled dynamical systems. There's a mechanical coupling between them in the form of actions that are employed in the environment, forces exerted on the environment. There's an informational coupling in that you've got information about the environment that's modulating the agent's behavior. And this sort of diagram may be obvious in present company, but it is still extremely an outside view in psychology, cognitive science, and neuroscience. Right? This kind of looks like not cognitive enough, okay, to people. So let's kind of trace around what's often called the perception-action cycle. So the agent or the individual, right, changes in their state, so an action, are some function of the current state of that action system and the incoming information, so modulated by the incoming information. That then generates forces, right, that are applied to the environment that changes the state of the environment. Might just be changing the eye position of the agent. That generates new information. So the environment is a dynamical system under the laws of physics, as is familiar. That then generates information. It might be optical information, acoustic information, haptic information if I'm pushing on a surface or hammering a nail. But there's a whole, these information fields just surround us. And that information is then used by the agent to modulate that, the dynamics of their ongoing action. And so it's that modulation which I think of as a control law, probably different from what an engineer thinks of as a control law. But essentially, you're using information to modulate a parameter or a state, right, of that dynamical system in order to adapt the system to the environment based on the information that you're getting. So these interactions, right, this local interaction has a dynamics of its own, okay, that behavioral dynamics. So it's basically just trying to measure the global behavior of this, the output of this system at a more abstract level so that we can track variables that are related to the task or the goal, if it's walking to a goal or if it's hammering a nail, right? There's some stable outcome, right, of these interactions, or an outcome the system is trying to stabilize. And so that outcome feeds back to modify these control laws. That's the lever that the agent has at its disposal to modify this whole system. And so you kind of converge on a stable solution, right, to your task, with hammering a nail. And so it's this sort of interaction that is that self-organizing factor. Okay? Based on the dynamics of the system, you're getting a reading of the outcome and then using that to tweak the dynamics a little bit. So the agent's just embedded in this complex system, and all the agent can do is tweak a little bit. It's got a few variables at its disposal in order to get out the stable behavior, the kind of intended behavior for that task. Okay, so that's the idea. And what I want to do is now try to go through a couple of case studies of this. Some of them are more fully analyzed than others. I want to look at rhythmic ball bouncing. This is kind of an extreme version of rhythmic ball bouncing. And then locomotor behavior. So the ball bouncing kind of looks at behavior at the individual level and tries to ask this question about how does information modulate the dynamics of a task like stable bouncing. And the locomotor behavior looks at this sort of phenomenon at both the individual and the collective level. And in particular, if you can track individuals through here, they're generating trajectories. But sometimes there are groups of people who are walking together, if I can see it. So there are groups here where they're coordinating their actions with each other. There's even this other species, right, that is coordinating its actions with respect to the obstacles and the people. So how do all these local interactions generate patterns, right, generate stable trajectories and coherent crowd behavior? So that's where we're going. But let's start with bouncing a ball on a racket. So Dagmar Sternad treated this, kind of came up with this task, which had been a robotic task, as a model for studying the dynamics of the interaction between an agent and the environment. So, I'm going to discuss here work with Isabelle Siglet and Benoit Bardy in France, and this is kind of an ongoing collaboration we have to look at this task. So the task is bounce a ball to a target height, okay? It's one-dimensional bouncing, so the ball, it's really just a timing problem. And it's period one bouncing, so there's one cycle of the ball for every cycle of the racket. And one of the things that an early paper by Shaw, Sternad, and Chris's original contribution to this, is that the dynamics of bouncing exhibit passive stability. So in a nutshell, right, if you're bouncing this ball to a target height, here's the racket. If the racket's behaving like a harmonic oscillator and the ball is making contact with the racket on the last half of the upswing, all right, when the racket is decelerating, right, toward a stop at the peak of the upswing, then bouncing will self-stabilize. So if you perturb the ball, right, after a number of iterations, so here's a simulation of that. If you perturb the ball after 6 or 8 cycles, it will kind of stabilize back to a stable one-dimensional bouncing. So more specifically, if the acceleration at impact meets this condition, so it's less than 0 but greater than this combination of gravity and the coefficient of restitution of the system, then if you hit with an acceleration within that region, right, the system will self-stabilize. So the moral that Dagmar took from this is that active control is basically unnecessary, right? We can just take advantage of the passive dynamics. And she even produced some data on this. So this is a 2001 paper. So this is the impact acceleration, and this is the variation, the standard deviation of the impact acceleration. And what you can see is that the data kind of clusters in this negative acceleration region which for this system was between -6 and 0 meters per second squared. And the behavior is very similar with eyes open or eyes closed, right? You don't need any active control. Once the system is stable, it'll remain stable. People who are novice bouncers, right, actually begin in the positive region, and with more practice, they move into the negative region. So they find this solution. And this is consistent with this idea that we just bounce passively all the time, right? We don't really need to apply any perceptual control. But when we began doing these experiments, we found that bouncing can be maintained outside the passively stable region as well, quite stably, but with positive acceleration values. And so that led us to think, what's going on here? Maybe the control problem is more complicated than this. So we started some experiments to look at whether control is purely passive or there's also some active contribution to control. And to do that, we set up a virtual ball bouncing apparatus. So here's the subject. They're moving a physical ping pong paddle with a tracker on it that is driving a virtual racket with a virtual ball on a screen, and there's a target on the screen. And so now we can play games with gravity and the coefficient of restitution and the motion of the ball's trajectory and try to open up this loop, right, and figure out what's going on. So for example, we did things like, here's the ball in flight, and at the peak of the ball's flight, we increase gravity. And so now the downward flight of the ball is going to take less time than the upward period did. And the next peak of the ball's height is going to be lower, and the natural period of the ball's bouncing is going to be faster, higher. And so the racket's going to have to adjust somehow in order to maintain bouncing, right, over the future. So we can do this in such a way that we can move the system into a stable state or out of a stable state and look if there's compensation only if the system becomes unstable. And we're going to do these sort of visual manipulations and then measure the adjustments of the racket, particularly the racket period, which should, if you increase gravity, all right, then the period should decrease, right, if it's responding adaptively to the ball, and vice versa. All right, so I'm just going to show you a couple of results here which bear on this question of is control active or passive. So here's the case where we increased gravity in this cycle. So this is the cycle of bouncing. This is the ratio of the racket period from before bouncing to after bouncing. And so it's 1 up here before the perturbation. Here we change gravity. And within the first cycle, there's a rapid adjustment of the racket in the right direction. In fact, it almost completely compensates for the change in the ball's flight. So very rapid, right? It's not self-stabilizing over 6 or 8 cycles. If we decrease gravity, we get the same thing, but in the opposite direction. So now the racket period increases with respect to what it was before. And in this kind of perturbation, these conditions destabilize the system. These kinds of conditions stabilize the system. And we're getting rapid adjustments in both cases. All right? So it looks like this is indicative of some sort of active control, right? Not just simply exploiting passive stabilization. So let's go through and kind of consider what the possibilities are that we've come up with for different kinds of control. Passive stabilization was Dagmar's first hypothesis, but we find these rapid responses and fast relaxation times that are inconsistent with that. That suggests active control, but if it was purely active control, as in some robot algorithms, that would mean you're actively regulating every cycle and just ignoring the passively stable region. But in fact, we human bouncers, especially with more practice, prefer the stable region. So they move to the stable region. Well, so what about some sort of combination like hybrid control where you're passive if you're in the stable region, but then you make active corrections if you're outside the stable region? But I just showed you that people make active responses to stabilizing perturbations as well as destabilizing perturbations. So it's not hybrid control. We think it's something that we're calling mixed control, where you're actively regulating every cycle, but you're doing so to stay near the passively stable region, presumably because that reduces the amount of control, that is the racket adjustments that are necessary and the magnitude of the racket adjustments that are necessary. So I want to suggest that this kind of mixed control regime is a general solution that exploits both the physics and the information in order to generate stable and adaptive behavior, because notice you're adapting to these changes in external conditions like changes in gravity or coefficient of restitution. So we end up with a kind of picture, right, that looks like this, where here we've got an agent coupled to an environment. The The agent is this racket that has a couple of variables that it can control. The environment provides information, in this case in the trajectory of the ball's flight, about the time up and the error from the target. And that information gets used to regulate the agent. So in other experiments, we found these very simple control laws that the timing of the racket period, okay, for timing control, the racket period is equal to just 2 times the upward flight time of the ball. So that's how you make those rapid adjustments in one cycle. And error to the target is corrected by not by computing the required velocity of the next impact, but the change in racket velocity from what you did last time, right? So if you undershot the target here, you must have hit it at a too low a velocity last time, so you're going to hit it at a higher velocity next time, and that's a simple linear relationship with the error. So these are very simple, right, little control laws, not computationally expensive, but they serve together with the dynamics of the system to keep it stable, right, and to keep it near this passively stable region. And this is the sort of mixed control where you're actively regulating every cycle to stay near to kind of exploit the dynamics. I think is a general solution that we've also seen in some experiments we've done on babies bouncing in a baby bouncer, okay, who very quickly zero in on the resonant frequency of the baby bouncer system, and in walking and running, I'd hypothesize. So let me turn to the second case study, and this is more up people's alley. This is locomotion. And I want to try to look at this at both the individual level and the collective level. So at the individual level, all right, so there's individual behavior, and somehow interactions among individual pedestrians generate these sort of collective traffic patterns, right, of crowds, which I think those patterns feed back to capture more individuals. And this is that self-organizing process that Herman Haken identified, a quarter century ago. So the question at the individual level is, how does a pedestrian generate a path through a complex scene like this? So I'm going to show here a street view of the Shibuya crossing in Tokyo, the busiest intersection in the world. And so you can see that the person with the camera is kind of bobbing and weaving through this crowd. They may follow another pedestrian for a period of time. They're actively avoiding, moving obstacles in clusters of people and coordinating their behavior to generate a trajectory, I submit to you, not pre-planned, okay, based on a complete model of the entire crowd motion. Right? So at the collective level, so here's a bird's eye view of Shibuya Crossing. This generates these amazing patterns, right? So if you look at the crossing phase, here we go, right? You get coherent crowd movement, you get lane formation, you get all of these patterns emerging out of these sort of local interactions between people, right? So how does that happen? And can we understand that just in terms of these local interactions, right, producing these global patterns and capturing the individual behavior? So let's start looking at, what I want to do is take you through the modeling cycle here, what Sumter et al. Call the modeling cycle, which is try to understand each of these pieces of the cycle, and if we can do that, maybe come up ultimately with an explanation of both levels of behavior. So I want to start at the individual level with trying to come up with an empirically based pedestrian model. There are lots of pedestrian models out there in many different literatures, from computer graphics to urban planning to simulation studies, but almost none of them are based on data, on individual human locomotor data. And so that's what we're going to try to do, is build an empirical pedestrian model. So here's the problem from Lucas et al. 1977. How do you steer through a complex changing environment like this, right? So, what's happening here? Well, there are all these obstacles, this dense forest. There's a moving target, right? This guy's chasing another biker. And there are other moving obstacles. There are other bikers trying to intercept this guy. He's trying to evade them. So it's a really complicated dynamic situation. And, are we using this sort of model-based control with explicit path planning, or are we just doing this on the fly, right, with online control, such that the trajectory that's yielded is just an emergent result of all of these moment-by-moment interactions? So what we want to try to build this model to see if it's sufficient, if an online model is sufficient to explain the sorts of behavior we see in human pedestrians. So our approach is to try to decompose the problem into a bunch of elementary behaviors, steering to a goal, avoiding stationary obstacles, but those things might be moving, right? So sometimes you're trying to intercept a moving target or avoid moving obstacles. You might also try to follow a neighbor, right, if you're walking together with somebody. So this list of behaviors might get extended, right? But we're trying to say, what's the minimal set we need to account for these kinds of observations? So here's the beginnings of our pedestrian model. How do we generate paths of locomotion? Well, our basic behavioral variable that we're trying to measure is the heading direction with respect to some target, all right? So if this is your goal, right, you've got a current heading direction here, and your task is to bring this error to 0, okay, if you're steering to the goal. If it's an obstacle, you want to increase that angle, but you don't want to keep increasing that angle or you'll spin around. So there's some dynamic here to how this angle is going to change depending on the goal's position. So our program is to measure a bunch of these elementary behaviors in people, model each one as a simple dynamical system, kind of inspired by Gregor Scherner's work on this in robotics, and then combine these components, linearly combine these components to try to predict more complicated behavior. So the lab in which we collect this data is this virtual environment navigation lab at Brown. So it's a big virtual environment, 12 by 12 meter tracking area. There's a tracking system in the ceiling. The subject is wearing a head-mounted display, so we can track the head movements with a very short latency, short enough that people don't get sick most of the time. And we can put someone in a virtual world that we can manipulate on the fly, right, to get them to interact with different kinds of situations. We can break the laws of physics and break the laws of optics in this virtual world, much as we did with the bouncing ball. So let's, I'm going to quickly kind of give you an overview of these components and then try to do something interesting with them if I don't run out of time. How do people steer to a goal, walk to a goal? So we're going to model this as just a simple mass spring system, where as the person walks forward, their heading direction is attached to the goal direction by a damped spring. And so as they move, their heading is pulled into alignment with the goal, and they end up walking in that direction. And so there's a kind of a potential function here, but the attractiveness of the goal depends on its distance. Okay, so as the goal gets closer, it gets more attractive. And so this becomes a nonlinear mass spring system, right, where the stiffness essentially depends on the distance of the goal. And so you get, I'm not going to show you a whole lot of data, but you get something that looks like this. Okay, this is a simulation of that component. And people kind of walk and then gradually turn toward the goal. But if the goal is closer to them, they're going to turn faster. Okay. Here's some human data on the left, what the model does to simulate that data on the right. So here we've got goals at different displacements from the initial direction of heading, and people make these sort of curved paths. They turn faster toward goals that are more off their path. The model does the same thing. This is time series of the heading error. And so there's basically an attractor in the direction of the goal, right? You're turning in the direction and stabilizing in the direction of the goal. And the model fits the mean human data almost perfectly. Not in this case, because that's the way the graphs are plotted. I mean, there is a delay, right? But we're not modeling that in this instance because there are no transients, right? The goals are there. The initial conditions are kind of given. We do add a time delay when we have moving things. So, but yeah, it's in there. I mean, it is there in the system. Let's do obstacles. So what's an obstacle? Well, it's just something you want to turn away from. So instead of having a negative stiffness term, we're going to have a positive stiffness term. So the spring is pushing you away from the goal direction. From the obstacle direction. But you don't want to spin around. Okay, so it's going to exponentially decay as a function of that angle. So as you turn away from it, the repulsion will decay to 0. And so you get this sort of potential hill in the heading direction that's pushing you away from the direction of the obstacle. And you get something that looks like this. So there's the person's deviating around that obstacle on their way to a goal. Data, again, on the left and the model on the right. So obstacles in 3 different positions. And you deviate depending on the position of the obstacle. The model does the same thing. And now the time series of the heading errors is increasing over time. So it's acting as a repeller, right? The obstacle direction is acting as a repeller of your heading. So now, if you kind of put these things together, you kind of linearly combine the obstacle term and the goal term, you can start making some interesting predictions, right? So this is what I think of as the behavioral dynamics of this whole model system. So these are acceleration vector fields. So here's your heading direction. There's the turning rate, and each little arrow is an acceleration vector. So if you're in different positions in the environment, right, say here, you're far enough away in this diagram that the obstacle isn't affecting your behavior yet. So you just have an attractor in the goal direction, the green arrow. But as you move closer to the obstacle, it starts to repel, right? So if you're in this region, you might be repelled one direction around the obstacle. And if you're in another slightly different position or with a different initial heading, you might be repelled around the other side of the obstacle. And so this is a bistable region. And so you've got an attractor on one side or the other and a repeller in the direction of the goal. As you pass by, right, you get a tangent bifurcation, and so now you've just got a single attractor again, but it's not in the goal direction, right? The direction you should go at any moment is the product of the repulsion from the obstacle and the attraction from the goal that gives you the direction of that attractor. And then as you pass by the obstacle, its influence disappears, and you again have a single attractor in the goal direction. So as you move through the world, the dynamics evolve, but as long as you stay with this attractor, right, you'll be kind of led by the nose through this complicated environment in real time, right, without planning your future trajectory. So let's get a little more complicated. What about target interception? We have a moving target now. Well, it turns out that humans, as we and other people have found, flies, dragonflies, bats, all use something called the constant bearing strategy to intercept a moving target. And this is familiar if you're a sailor, right? If you have a moving target, what you want to do is sail so that the target remains at a constant compass bearing, right? And in that case, you're going to collide with this other boat. And that is what all these animals do. And so we basically use the same structure of the model, but now you're nulling change in the bearing direction of the target rather than the angle of the target. And that gives you trajectories like this. So if one person is trying to intercept another person, the interceptor is moving on this path that turns onto a straight path to intercept the target. So the interception path is now behaving as an attractor. Here's some data on the left. So here's a moving target. Here's the path of the human in red and the model in black, which you can't see because it's basically right on top of the human data. And the time series of this heading error now, which now goes up to some constant value at which you're on an interception path with respect to that target. So people indeed do this. They turn onto straight interception paths ahead of the target that lead the target. And it's fairly, again, simple descriptive model of that behavior. For a moving obstacle, again, we just flip the sign on that stiffness turn. So now you're repelled away from the interception path with an exponential decay off to the side. And you get, there's a moving target, and now we're deviating around the moving target to get to the goal. There we go. And here's some human data and models. So here are moving targets of various speeds and trajectories. There's a goal, and the human in the solid curve deviates around and switches to deviate around the backside of the moving obstacle if it's going faster, and the model switches at the same point. So there are these sorts of, the switching behavior is captured by the model reasonably well. Finally, if we're interacting with other people, right, like we might want to follow our neighbors, we need to control our speed in order to do that. And so we did a whole bunch of experiments about how one person follows another, and essentially they serve to match the speed of the leader. And they do this by nulling change in the visual angle of the person in front of them, okay? And so if you build that into the model, you get this sort of speed matching behavior. So now they're traveling at the same speed. This is the follower and the leader. Interestingly, they don't, necessarily walk. They don't zero the distance between them, right? They match the speeds. And so depending on the initial conditions, you might be walking a little ahead or a little behind of your neighbor. And similarly, you've got to control your direction, right? Your heading, so you're controlling your vector of walking. And so in this case, we're nulling the difference between the heading directions of the follower and the leader. And we've collected data on this, but haven't validated this particular model yet. But so the follower turns to match the direction that the leader is going in. And this basic sort of speed and heading matching or velocity matching will generate coherent crowd behavior. But there's one last piece, which is you don't want to run into people, right? If the person in front of you suddenly changes their speed or stops or something, you need to brake. And so we borrowed David Lee's tau dot model for which gives you a constant deceleration to a stop in front of an obstacle. And we did some earlier experiments on that in humans. So humans also do something like this, right, in order to stop before colliding with an obstacle. So now we have the elements of a pedestrian model that's empirically based. Seems to do a good job at accounting for human behavior. It's kind of a descriptive model of these things. But now if we start putting these components together, can we explain more complicated situations? So we're going to now go look at this sort of collective crowd behavior as exhibited by these starlings, okay, which have these amazing murmurations, right, which create coherent motion of an amazing variety. But I think humans do this too in Shibuya Crossing, right? So they're doing that sort of coordinated motion with large numbers of people that somehow arises for free. So can we account for global behavior like this as arising from local interactions? And in particular, if we try to use multi-agent simulations based on our pedestrian model, can we generate the kinds of traffic patterns that we see in human crowds? And the questions we want to ask are, can we reproduce individual trajectories? We're just beginning to evaluate that. Can we reproduce these global patterns? And what is the minimal set of components that's necessary to do so? So that's the kind of game we're playing, the modeling game that we're playing. So we're now moving around this modeling cycle, right? So we've got our pedestrian model. We're now going to simulate their interactions with multi-agent simulation. But we need some human crowd data to compare our simulations to. So last summer, we took over a big auditorium or a big hall at Brown, Sales Hall, and recorded groups of up to 20 people walking around in different scenarios that we kind of specified for them. So we set up a motion capture system. Everybody wore these silly antennae with reflective markers on their heads. And so we had a whole bunch. We did this for like 4 consecutive days and had to set up this thing and take it down, collect all this data in a week. And so we're still going through it. We're still just processing this gigantic amount of data that we collected. But we have some early results. So we're going to ask people to behave in certain scenarios, and then we're going to see if we can model them. All right. So here's an example. This is the Grand Central Station scenario, like on my first slide. We're trying to simulate a condition like that, where there are people, in this case we had 20 people crisscrossing the room back and forth to targets we gave them on the other side of the room. They had to avoid these stationary obstacles, and they had to avoid each other, okay, as they moved. And so this went on for 3 minutes at a time. And this is the start of the data collection. This is the tracking data on the right. So we get some loss of people as they move out of the camera volume, which has, for modeling purposes, is creating some problems, but we're working with that. And so people just do this back and forth for 3 minutes. We collect this volume of, all kinds of things happen, interestingly enough. Traffic patterns get established. So some routes are followed more heavily than others based on the geometry of the obstacles. Okay, so here's an attempt, right? This is our first attempt at simulating some of this data. So here's on the left just a replay of the data from one trial. And you can see the virtual humans are blinking on and off as they move out of the capture volume or as we lose tracking. But you can see over time, right, these trajectories build up and establish certain kinds of traffic patterns in the room. And the simulation of that trial is on the right. And so we're in the process now of trying to do some divergence measures of all of these trajectories over time to see how well at the trajectory level we're capturing the traffic patterns on the left. But so far, right, just using, in this case, the goal obstacle, moving obstacle, and that emergency braking component, we can generate quite similar individual trajectories and get these traffic patterns, which are very similar to the traffic patterns we saw in the human data. So on each pass, right, we're initializing the model with the initial conditions of the human as they enter this tracking area. So more interesting, perhaps, is this sort of swarm scenario, where now we're getting coordinated behavior among this group of 20 people. And in this case, the instructions were simply to, I want you guys to walk around the room, okay, randomly veering left and right, but stay together, right, as a group. And so this is what they're doing. We lose some people sometimes, right? They kind of veer off and then end up rejoining or getting picked up later. And the tracking data, for example, are on the right. So they're fairly coherent motion. They make turns, have straight sections, and so on. And so we're beginning to, again, analyze this sort of tracking data. We've tried to simulate this in a couple of ways. So one of the key issues for collective animal behavior is, what are the local rules that generate those starling flocks? And there's some physical models that suggest that simply heading matching is enough, right, to do it. And so we're trying to play around with what are the actual components that are necessary to simulate human crowds. And so we started out on the left just with alignment and speed matching and treating each other as a moving obstacle. And you see what happens, it just blows up, right? So when people are in a crowd, they're no longer treating each other as obstacles, right? So there's got to kind of shut off that component and turn on some other component. And so when we remove the moving obstacle on the right, then we're getting this sort of coherent crowd behavior emerging. So basically, heading alignment isn't enough because that assumed, so Vishek assumed that every person was going at the same speed, but we're not. We've got to control our speed as well. So we need both this heading alignment and speed matching components, and we have to have this emergency collision avoidance so we don't run into our neighbors if they stop. And so the swarm, I think this sort of swarm behavior involves a kind of switching from moving obstacle component to a following component. So we also set up that sort of lane formation scenario that you saw in the Shibuya crossing, where we had two groups walking toward each other and passing through each other. And so here's an example of that. So they're just kind of random groups, and they manage to get through each other. But notice these lanes form rather spontaneously and persist for a while, right? So, and this could result, right, from this sort of following behavior combined with that obstacle avoidance behavior. And on the right is the tracking from, this is a group of 10. It's counterflow with another group of 10. And again, you see that sort of, they break up into 2 or 3 lanes. And so on the left, we have the data replay of a trial of 10 versus 10, right? And you can kind of see, with some tracking problems, you can see these things, lanes forming. You can see that in the traces. And then when we use the alignment, speed matching, and collision for each group, and anyone with motion that's opposing your motion, right, beyond 90 degrees to your motion, is treated as an obstacle. And so it ends up that the opposing group are treated as obstacles. And that's enough to kind of form the same set of lanes that we saw in the data on the left and get this spontaneous lane formation just out of these local interactions. So I want to go now to this question of how does that coordination in a crowd actually form, okay? And if we see this in a swarm of fish, let's see if I can play that again. This fish goes from a kind of a loosely organized shoal into a coordinated school as a predator approaches. And you can see that transition happening in that footage. The fish are kind of milling around and then they cohere into a more coherent school. So somehow these global patterns form and propagate through a set of individuals. There's some coupling between them, right, this visual coupling in the case of humans, that captures more individuals so that pattern spreads. And so what we're trying to do now is say, all right, once these interactions begin to happen and behavior becomes a little coherent, how does that pattern spread, right? What is that pattern of coordination? How does it capture more individuals to create a coherent swarm? So we're trying to now develop some measures of coordination that we can apply to our data. So we're basically going from a bunch of individuals, right? In this case, with 4 individuals, each having 2 degrees of freedom. We have an 8-degree freedom system that's now getting condensed down into a 2-degree freedom system with a common direction and a common speed. So there's this dimensional compression going on, and we can see that if we use PCA, for example, on our data, we get that kind of dimensional compression. But more interestingly, I think we're beginning to do these sort of pairwise statistics between people in the crowd. Yep. Yep, I'm almost there. But I get that 20 seconds that you just took away from me. So pairwise statistics. So we're measuring, say, a focal individual, maybe an individual at the center of the crowd, and looking at how they coordinate with each other member of the crowd. So measure the difference in heading between these two individuals. So you get a time series of the difference in heading, or between those two individuals or those two individuals. And so you can kind of build up what this coupling field is like between individuals. And that's what we're plotting here. So this is for a total of 6 minutes of swarming data. We look at the individual in the center of the crowd and measure these pairwise heading differences between all other members, and then average them over this giant set of data. And essentially what you see is that central person is strongly coupled to its near neighbors. But about 2 to 3 meters away, that coupling strength dramatically weakens. And so there's a strong local coupling, right, that falls off at about 2 to 3 meters. So you're coupled weakly to your neighbors. And so so there are interesting questions here. Well, does that depend on density? How many neighbors are you coupled to? Or is it a fixed number of neighbors, or are you coupled to everybody within this radius? And those sorts of questions are going to have a great impact on how that coordination pattern emerges. And so that's what we're kind of working toward. So our next step in this is to have a human subject walk in a crowd of virtual agents, okay, virtual humans. And so now we can manipulate the crowd around the subject and try to test how they're responding to different types of manipulations. So we can vary the speed of the neighbors, the heading of the neighbors, how many neighbors agree with each other, right? And how big the influence of these is on people as a function of distance, the function of the number of neighbors. So we're beginning to run these experiments to try to map out this visual coupling field. So I'm going to end now with claims, okay, not conclusions, because this is still kind of in process. But so far we're showing that an empirical pedestrian model can account for individual locomotor behavior. So at the individual level, the model, if people do what the model does, the agent just tracks a locally specified attractor as the dynamics evolve, and that leads them on a trajectory. So the trajectory emerges in an online fashion without having to do any world model or explicit path planning. And then at the collective level, we're showing that a few components of coordination are sufficient to generate these global patterns of crowd behavior just based on these local interactions. Humans seem to achieve stable adaptive behavior by using information to modulate the dynamics of the system in which they're embedded in both of those ball bouncing and locomotion cases. And so I think behavior arises as a stable solution of this whole system's dynamics. And that's the sense in which Gibson was right, I think, that behavior is regular without being regulated by some kind of central intelligence. Thank you.
We're going to do questions without microphone, and I think we're going to try this for the rest of the meeting without microphone. So you just raise your hand, or if you're really excited to bring something out.
Are you going to call? You can call.
I'll call. Hi, Joe. Great to see you.
So this sounds like a math question, but I think there's a conceptual issue. So if you take something like two groups passing through each other, that's very degenerate mathematically. There's a lot of solutions to that. Okay? So first of all, experimentally, that makes me wonder, how are you going to decide whether your model is good or not? Yeah. And because it's not a priori obvious, and in fact, possibly, I would guess maybe ill-advised compare trajectories, maybe unique. So that's a question. But really, I'm interested more in the psycho-perceptual aspect of this. How do you think that kind of degeneracy of solutions, what role do you think that plays in these perception action processes?
And your task first is to
repeat the question.
Oh my God, I'm sorry about that.
He doesn't have to repeat it.
So as I understand, Joe, what you're saying is there's a degeneracy problem. So as multiple individuals are interacting with each other, there are a lot of possible solutions. There's probably no closed form solution. And it's all highly dependent on initial conditions, so it's right. So it's really, and so we're trying this at two levels, right? So we're interested in the individual trajectory. So we want to do like statistical mechanics where we can predict the particle motion, right? Probably a tall order. But if we can, approximate the initial conditions of each particle, and we can have some estimate of noise. We've been playing around with adding noise to the model in various ways. How does it break down? When do the trajectories change? So we're just going to see how good we can do. So one of the techniques that's been used in simulation in kind of agent-based simulation is to look at the divergence of the model from the data, right? And so you initialize the simulation, and you measure, okay, the trajectories are separating and separating and separating, and at some point you set a criterion, you say, all right, it's separated so much that I'm no longer predictive. Now I'm going to restart, all right? And I'm going to do it again for the time step n+1 and kind of keep doing that and get a measure of the time over which you're making good predictions. So that gives you a way of estimating in a whole family of trajectories, how well am I doing at the individual trajectory level.
I would guess that there's a subjective correlate to that, though, for the agent, right? Because that degeneracy and that inability, there's something, I don't know what it is, but that's why I was dumping it on you.
Yeah, I know. Well, the thing that I've been amazed at in our studies of individual people's trajectories is how regular they are, right? People are really regular. And you get, I don't think I showed a graph of this, but if you plot all the trajectories of like a dozen subjects with 100 trials apiece, there are these families of trajectories that are really tightly related, right? And so I don't know, so how much noise is there? There's got to be some biological noise, but at the level of the trajectories, it's amazingly regular. Now, but every obstacle creates a bifurcation, right? An opportunity for a bifurcation. So little bits of noise, as the scene gets more complex, you get rapid divergence. So, we'll see how that works out.
Behind Art, I don't know your name.
Jim. So I was wondering what kind of interesting glitches you've seen with your model. The first simulation of pins, I noticed 3 people who walked up to a pin, stopped, and walked straight through it.
Oh, they shouldn't have gone straight through it. That's a graphics issue, I think. Yeah. So I mean, so what kinds of glitches? And they're interesting glitches, right? Like, the question was, thank you, keeping me on the straight and narrow. The question was, what interesting glitches have you seen in the modeling, right? And for me, the most interesting glitch so far was that explosion when we tried to simulate the swarm. And I just assumed people were going to be avoiding each other, right, in this crowd. But the whole thing just blew up. And so that was really interesting because it suggests, again, there's some whatever phase transition is going on between, a shoal of people and a school of people, right, has to do with you're treating your conspecifics differently, right? So you're no longer treating them as obstacles, you're treating them as neighbors or something that you're going to follow, right? And that's obviously where a lot of social influences can start to play a role too. So that's one interesting glitch. I mean, the thing that I've been, we've been struggling with moving obstacles because that's one of the few cases we've seen where pedestrians actually vary their speed. Under almost all these other behaviors we've looked at, people adopt a preferred walking speed and just go, right? Probably an energetically preferred speed, and they just keep walking at it, except when there's a moving obstacle. So people do tend to slow down to avoid an obstacle that's about to move in front of them so they can go behind it. And so that's kind of led us into now creating a model of speed control as well, which it turns out is proving useful in the swarm situation. So that was another glitch, right? We were modeling this as, I guess 2-dimensional data when it was actually 3-dimensional data. So we had to figure out a way of dealing with that.
Way in the back.
For your first example of bouncing a ball on a racket, you led up to this proposed mixed control scheme with a simple relationship. But then you ended and you didn't present any experiments or any data.
Yeah, right on the time.
Can you talk about the results of that?
Yeah. So this is in terms of the visual information that's used to control the racket motion? Oh, okay. Yeah. So I had actually, sorry. Let me to see if I can get back to that in a simple way. Well, so I had just presented some data which bore on that question. So let's see, I'm trying to get back to that. So the question is, what's the evidence that it's mixed control and not something else like this hybrid control? I guess I'm not doing this very effectively. All right, I'm bombing out of here. Okay, so yeah, so we kind of went through this set of possibilities. And so the evidence for mixed control, so in what I showed before, maybe I should flash back to that. You know, there's some combination of these two things. So there is obviously active regulation that we showed, that I showed briefly in that data, but they're also remaining somewhere near this passive region, probably because it minimizes the amount of adjustments or the magnitude of the adjustments that have to be made. And so they're combining these two things in some way, right? And so with hybrid control, you might, if you're stable, do nothing, right? But if you become unstable, then you might make an active adjustment, right? Or in mixed control, you're always making active adjustments. You're just doing so in order to stay near the passive region. And so the evidence against hybrid control was this, which is that when you change gravity in such a way that it stabilizes the system, you also get an active adjustment, right? So if you were in that sort of hybrid mode where you'd say, all right, if I'm stable, do nothing, right? This shouldn't have led to an adjustment because it's actually making you more stable. And yet, people were monitoring that cycle and making an active adjustment to it, despite the fact that the perturbation or the change in gravity acted to stabilize the system, as opposed to destabilize the system.
Yeah, if you decrease gravity, it's not going to make the ball stop bouncing. It's going to increase the period, right? And you're going to have to change something, otherwise you're no longer bouncing the ball at the period of the ball.
Yeah, but you don't have to do it in the first cycle, right? So what the evidence I think here is showing is that people are monitoring every cycle and making immediate changes, right? So you could, if you're in this passively stable. So let me just say we also saw the same thing with changes in the coefficient of restitution, which don't require an adjustment in the racket period. Yeah.
It sort of was implicit, the way you presented the problem, that you thought people were trying, one of the main goal was stability of the bounce.
Or to keep it going. Yeah.
And so you've made this more stable,
yeah.
And yet people have changed their strategy. So it must be that there's some other goal that in the cost function that, and when you change the environment, the optimum of that cost function is changing. That change has to be due to some other goal, right? So what's the other hidden goal that we haven't talked about in this conversation?
Yeah, so the question is, why are people changing their racket motion when the perturbation makes the system more stable? What's the other goal, right? If the goal isn't simply stability, what's the other goal? Well, there's two goals, right? It's to keep the thing going and to hit to the target height, right? And so well, you could keep the system going without reaching the target height, right? So you have to satisfy two criteria. So I mean, this is a longer conversation. I think what I should do is pull out the data where we perturb the coefficient of restitution.
If it gets interesting, we have to flip it off.
Good. Okay. Hi, Art.
The short version of my question is, am I smarter than a fruit fly? And so, no. Short version of the question.
Yeah, and I would say not by much.
Okay.
Yeah.
So it's very appealing to me to think in terms of these sort of simple local control laws. But in my daily life, I don't feel like that. I feel like I'm always anticipating what other people are doing and doing all sorts of planning. And maybe that's because I'm paranoid or schizophrenic or something. But, you know, I think about things like, oh, if I speed up, then the person in front of me is going to hold the door open for me. And so I'm going to sort of draft off of them. And also, for me, sailing, I'm a poor sailor. Sailing involves a change switch modes and think, oh my God, this actually worked, this is incredible. And so shouldn't that be natural to me if I were doing that all the time? And also, so I think often we like to give a lot of credit to the central nervous system. And so I'm usually arguing with people about, oh, I think there's a simpler explanation. You don't need this complicated thing. But this is a rare circumstance where I'd like to think that I'm smarter than you.
Yeah. So you're reversing your position. So that's good. So aren't we smarter than a fruit fly, right? Aren't we smarter than a fruit fly? And my answer to that is we're basically just human flies, right? But we're smarter because we're more adaptive, right? So we have the capacity to learn dynamics of new tasks, which a fruit fly isn't very good at doing. And so if I give the fruit fly a ping pong paddle and say bounce this thing to a target height, it's not going to happen. But so maybe a big part of what the nervous system is doing is this sort of exploration and learning, right? Discovering these mappings between information and the free parameters of the dynamics in order to control more and more novel systems, more and more complex systems. But once you get it, as you just described it, it's like, oh yeah, that's really simple. I'm going to go with that. Then you can kind of automate it, right? It doesn't take your central resources to walk in a crowd, right? You can be thinking about the theorem you're trying to prove while you're walking through the crowd, and you still won't run into things.
We're 1 minute over the 4 minutes overtime, so we're only going to go 30 seconds past that with one question.
So how do you have a suggestion for the inverse problem where you want to guide a crowd in a particular way, like for example for rescue scenarios or evacuation or mass events?
Yeah, so is there a way to, is there a way to guide a crowd, right? If you're trying to if you're worried about evacuation so there was a case in Rhode Island, my home state, the infamous station nightclub fire, where there were 3 exits, right? But everybody came in one door, and everybody tried to get out the same door that they came in, right? So can you avoid that sort of situation? And that's my hope, right? 100 people died. Right? Yeah, 100 people died. It was a huge disaster. And so could you, for example, set up an environment that would split up a crowd, right? By placing obstacles in the right position. I think we can model that sort of thing. There's also some interesting evidence that if you want to lead a crowd, it takes 3 people moving in the same direction, right, to influence the behavior of enough neighbors, right, to lead the crowd in a new direction. So that has something to do with this top-down capture of individuals, right? If you create enough of a coupling, right, that's aggregated over enough people, you can move a crowd. Okay. So thanks again.
Okay, so I'm here to talk about a new 3D dynamic walking robot. This is a conference on dynamic walking. This is primarily supported out of Gil Pratt's M3 program. Jonathan Hurst is the PI. Hartmut Geyer and I are co-Is on the project. The objective is to demonstrate agility and energy efficiency in the same machine. And of course, we're trying to go at it using dynamic walking. Ultimately, these robots should be operating outdoors. My previous robots have all been tethered to a boom, not outdoors. This one is supposed to eventually get outdoors. So Jonathan has built already 3 robots and delivered them to Carnegie Mellon. You've seen it in the lab tours. If not, you will see it soon. He's kept one at Oregon State. Those 2 robots will remain on a boom for at least a short period of time. And he's delivered one to Michigan, where we have it off the boom. A little something about the robot, roughly 55 kilograms in mass. The floating body model is 16 degrees of freedom. So in single support, it's either 13 or 12, depending if yaw is restricted or not. There are 6 actuators, so the legs are formed by a parallelogram, so it's a very special 4-bar linkage. And so the drive in the sagittal plane is a series elastic mechanism. You can see these springs that are in between the output of the harmonic drives and the upper 2 bars of the parallelogram. And so if we have feet, they are passive. There's no actuation there. Brushless DC motors, 50-to-1 harmonic drives in the sagittal plane. The lateral direction is a cable drive with roughly a 27-to-1 gear ratio, and it can be operated on its own because it can carry a set of LiPo batteries. So that's the robot. And this is just to show from behind that it really can stabilize itself in 3D because the hips can move outwards. But the hips do not have a twisting motion, so turning will be a little bit slow with this robot. That's the basic machine. The sensors on it, very minimal at the moment. It has encoders pretty much everywhere you would want one. There's an IMU mounted in the torso. Limit switches on joints for safety to try to soften things up before you hit a hard stop, but that's it. There's no sensors in the feet yet, etc. Okay, so that's the robot. How are we going about doing its feedback control? A lot of you know me, and I have a particular method, and yes, that's what we're trying to apply, virtual constraints. Bobby Gregg gave a very nice introduction to it yesterday. I'll give a slightly different introduction. So if you've had the pleasure of seeing the mechanisms of Theo Janssen, his kinetic sculptures have dozens of legs, hundreds of links, and they're all synchronized to a single crank. So I call those physical constraints because they're imposed by how you connect the basic bars in the robots with joints. If you now remove those connections to the crank, install actuators and sensors on his machine, for example, and then set yourself up a feedback problem where you try to drive this quantity to 0 using a feedback law, then you will actually impose the same constraints that Theo Janssen had. The benefit is, if you do this with virtual constraints, you can reprogram on the fly where he has to get out a hacksaw and glue and put things back together to get a different gait. Theo Janssen's very clear what his crank or phase variable is. Bobby was talking about using the center of pressure on a foot. What we've been using, because we've mostly had point feet robots, is the angle from the toe to the hip. It gives you a roughly monotonic, it gives you a monotonic quantity, and we use that to synchronize things like the knee angle, hip angles, etc. throughout the gait. So we use these virtual constraints for synchronization and control. How do we design the desired evolution? Just very quickly, we have our phase variable. We have a set of free parameters. These might be Bezier polynomials, NURBS, your favorite set of functions, sines and cosines, I don't care. We set up an optimization problem over a gait cycle where we minimize something like cost of transport, subject to constraints such as a walking speed, ground reaction forces, foot clearance, limitations on torque of the robot, etc. That's how we do it. Here's the virtual constraints played out at Oregon. We showed up on a Sunday night, went to the lab. They were still building the robot. We said, this is not a good sign. Showed back up on Monday, and they were ready for us. So the guys worked really hard overnight. We spent Monday getting our software in the ROS system, and by Tuesday, we're able to play out the basic virtual constraints. And then the next day, we have a stable gait on the robot. So it's walking at roughly a meter per second, 0.95 something. Using onboard power here, computations on board in ROS. Okay, so I like this hybrid zero dynamics approach using virtual constraints because it allows me to break my feedback design problem down into two parts. The first part, driving the errors in my virtual constraints to 0, is more or less a classical feedback problem you can approach in many different ways. And then once the virtual constraints are imposed, I get a restriction dynamics. And if I've chosen my virtual constraints correctly according to the anatomy of my machine, then I get something interesting. So for example, on Mabel, the restriction dynamics is something like, this does not mean diffeomorphic, but it's approximately equal to a slip-like model, but it's a distributed mass, distributed inertia, there's losses in the spring, the stiffness varies throughout the gait, etc. But it's slip-like, it's more complicated, and that's what gives you this crazily dynamic behavior, where it runs very fast, as Bobby showed yesterday, can handle very rough ground. Here's the students just putting things down randomly. Ollie wasn't very nice to the robot, handled it anyway. It's a 20 centimeter step down. The robot does not have a camera, doesn't know where the step down occurs. It cannot see these obstacles. There's a sensor on the front of the foot that when it closes, it knows it's bumped into something. It's a finite state machine running. And it does foot placement as best it can to keep itself upright. So those are the things you can do using virtual constraints. Highly dynamic behavior, and that's what we're after. Okay, so here's MARLO. That's the Michigan copy of the robot. We have put prosthetic feet on it simply because to initiate gaits, we want to start from a standing posture, and on point feet, that's hard. And with prosthetic feet, that's a little bit easier. So they're not actuated, they are passive. We've really splurged and have an expensive IMU on there. We've got our theory extended to work in 3D. We've done simulations with a compliant ground model that has stiction and slipping, etc. in it. Applies ground contact forces to the four corners of the feet or not, depending on how they are in contact. So we've checked out our theory. It's quite robust. And so then we've started experiments. And we're not quite there yet. Okay, so it's slow motion here. Gait starts, initiates well. We get the rolling motion. Foot placement's a little short there. Pretty good here. Pretty good here. Another bad foot placement, leg exchange. We break ground reaction forces. We fall forward in the sagittal plane. Our longest is 7 steps so far. These are all 5. I'm kind of showing typical. Nice foot placement. Short again on the right. And then we don't do leg exchange and we fall in the sagittal plane.
This is a controller that works well in simulation?
Yes. Thanks for the... Yeah. So that's what I plan to do in this slide, and I've got 1 minute, right? Yeah, so thank you. So where we're having trouble, I mean, I am enheartened by the fact that we're not falling sideways. Our lateral stabilization, at least on these initial steps, where it's really slow and really hard to do lateral stabilization well, is working. The primary reason we're falling, kind of disheartening, is that we are doing very bad job on stance to swing transition right now. And I think it's because we're undersensed. We're using the spring deflections to detect loading on the legs. It works really well with point feet. All that's what I showed you in Jonathan's lab, and then again in my lab was using point feet. You get a big enough spike that you see that super clearly. And the other thing about point feet, well, yeah, it's on the ground. Where do you want to rotate? Well, yeah, it's now time to transition. This one's on the ground. With feet, it's less clear. This is something we haven't talked a whole lot about at this meeting, but you know, just because you get the heel down is maybe not the right place to start the gait transition. You want to get a little bit more weight transitioned into it. That takes finer knowledge than we're able to extract from the springs. So that's one of the reasons we're having problems. So we're going to have to put some sensing on the feet and do a better job there. The other thing is I've coined a new term. You know, I use virtual constraints. Go ahead, ding, please. Please. Okay. I use virtual constraints. Now, if you don't zero out those things, I'm calling them virtual suggestions. And right now, we don't know this robot well enough to really get our local feedback tracking is not very good. So, you know, on good days, their errors are down in the 2 and 3 degrees, and in the afternoon, they might be in 5 degrees, but there are other experiments where you might see an 8 or 9 degree error on leg angle or something. And well, what that means is that you have really bad leg placement, not because you didn't want to put the leg in a good place, but because you realized a bad leg placement. So we will get that. Part of it is the torque limitations. We haven't modeled the harmonic drive, so we will work on that as well as we're getting sensors on it. Questions? Well, why not give what we're doing a shot before we throw it out the window and try something else, I guess would be my answer. So I think for doing basically sagittal plane motion, if you're either going to synchronize the time or to a phase, as Andy and I have been talking, I'm very comfortable with lots of experimental practice on synchronizing with phase. The roll motion needs to be coupled to what's going on in the sagittal plane anyway, and so I think that's why I want to do my leg placement adjustment as a function of my mechanical phase variable. Now we're going to get beyond this, you know, stable sagittal motion. That's going to happen. We are going to get it. And then we're going to start looking at lateral motion. Well, when I'm doing lateral motion, my current mechanical phase variable is doing what? It's completely out the window. And so then we got to start thinking about, do we want a library of behaviors with different mechanical phase variables associated with them, or do we use other means of doing gait synchronization, like fundamentally going to time? I think that's the point, Art, where I make that decision. Yeah, that's an interesting thought. I mean, where we parameterize our Bézier polynomials, it doesn't have to be a single phase there. It could be the roll motion as well of the robot. But we don't see a need to go there for what we're trying to get to just prove to ourselves that the robot is working properly. And then when we get the more dynamic things, as each of the students gets their thesis, I think things like that we have talked about, and I think they are very good to do. I agree. We have problems with yaw when we have really, really bad foot placement. So we had 8 reasons for having swing leg retraction. Let me add a 9th one. Okay? If you're walking and you scuff like this, huge yaw. If you come forward and you still haven't done your leg retraction, but this is trying to come back and this is going forward, you don't have yaw. That's the 9th reason to do swing leg retraction. So we're doing more or less some swing leg retraction. We have very little yaw torque at leg touchdown. That's why the robot is not twisting. Now, we've had experiments where we screwed that up, and then the robot goes like this. We're going like, whoa, how'd that happen? And Huang Park explained it to us. No, it's just inherently in the zero dynamic. I mean, if I gave a perturbation to yaw, it would then should try to start just walking straight along that new alignment. We're not doing any event-based control for yaw. You know, we want to get 20 steps. We shouldn't need any yaw control. Please.
In the discussion we had before, I thought I had a little insight, which I thought was illuminating, so I would like to share.
Okay.
Which is that ultimately, from you have perfect knowledge of state. I think a very good controller would be some nonlinear state feedback, where given the state, there's some function that tells you what percent of your control. And if you had a good model of the system, you could do some optimization and find the perfect policy for whatever your optimization criteria was. And I think one way of thinking about this hybrid zero dynamic or using a phase variable is the same as using Hartman's event-based reflexes, which I think many of us are doing, which is ultimately we're trying to approximate some good state-based feedback, and we're trying to find shortcuts for the representation of the state. So one shortcut is to have events, which are just sort of very, very low-dimensional representation of the state, and another strategy is to take a phase variable as a proxy for the whole state. Another would do what Art almost suggested, which would be to say, have two phase variables, a leading phase variable and a fall forward and backward phase variable. But still, the same thing is happening, which I think almost all of us in the control business, except for Chris Atkinson, are doing, which is just to find some lower dimensional representational state. And this is just one way to do that.
Well, I've had a lot of success doing that one, and that's what I'm going to stick with for a while.
I'm not criticizing, it's just
Yeah.
a way of thinking about what it is.
Please. I'm having trouble, well, I'm having a little bit of bad foot placement from bad tracking control in the hips and stuff. So that gets, and then I'm not transitioning properly. I'm not, you know, stopping this one from being swing phase and making it start taking the load and then transitioning. So I'm having problems there. So I think the question is, can I do more robust design of my desired trajectories? Yeah, okay. So the answer is I think I can. My simulations say that I shouldn't have to. I mean, I shouldn't have to be so uncertain about when to transition on gate. And this is something, you know, everybody here assumes when they're giving their talks with these with their simulators that they know when to transition from stance to swing. And we had toe sensors on Mabel, which made it very clear when to do that. We don't have adequate sensing. So I think really the solution is better sensing. But no, it's in my PD controller. So remember that robot was supposed to deliver 60 amps of current to each motor, but they're currently limited at 30, right? So by the time you go through the harmonic drives, I've got maybe 110 Newton meters, but I've got stiction giving me a backlash effect. So my tracking errors on my joints is where I'm having a problem. I'm reading it. No, the resolution is down to the micro degree, so I can see all of my error, but I can't do anything about it.
So I'm a professor in mechanical engineering department at Carnegie Mellon, and today I'd like to talk about our leg robotics activity in our lab, which is called Nanorobotics Lab. So my lab is specialized in small-scale robotic systems and locomotion at a very small scale in the sense of palm size. So these are our lizard-inspired robot, this is gecko-inspired robot, and this is insect-inspired water surface locomotion system, flapping wing-based flying robots, surface locomotion-based locomotion systems inside the body for medical applications. This is a soft rolling robot. And even we have robots down to micron scale. So these are, I think, could be interesting for this community because these robots can crawl on the surface using slip dynamics at the micron scale. And this is a bacteria-driven swimming microrobot for a swarm of microrobotic systems kind of applications. Today, I want to focus on one of our activity, which is surface locomotion on water surface. And if you look at animals doing this kind of locomotion in nature, you see many insects which live on the water surface. So these guys can always stay on the water in a stable manner, like fishing spiders, water striders. And then and lizards and some birds and fishes also do the water surface locomotion for different reasons. We looked at in my lab first the static water surface locomotion where you can stay on the water and these insects use what we call repulsive surface tension. If you look at their legs, they are wax-coated, hairy legs which repel water very high, and that repulsion is good enough to lift the insect body weight, and that gives the static stability in the sense of lift. For propulsion, if you look at this infant insect, they can use sculling motion to glide on the water surface. This is the most power-efficient and elegant water surface locomotion that we took inspiration, but of course, as you see, the real robot doesn't look like the insect necessarily, but it uses the same physical principle of static equilibrium with surface tension and then dynamic propulsion with sculling motion. But more interesting for this community is this lizard that can run on the water in very complex environments. So looking at this video from nature, you can see that this animal can run on running water, which is a river, which is very, as you saw, a lot of disturbances. And in this case, the question is how this lizard lift its body weight and propel forward. And the short answer to that is different than the insects I showed you. This lizard is big and heavy. It doesn't use any surface tension type of principle. And it needs to be only fast and running always, otherwise it will sink. So biologists at Harvard looked at that problem before. And this is a biological experiment from side view. You see the lizard on the water surface, creating this air cavity, first slapping the water surface. And that slapping impulse can create you some vertical, also positive force for lifting. And that's momentum transfer. And then the second part, which is the more dominant part, is the part where the food is under the water, creating this air cavity, and depends on the shape of the food and the height underwater and the speed of the motion and the trajectory, you get a drag force. So this drag force vector, as you see with the given trajectory, is perpendicular. That means it has component for lifting and component for forward propulsion. And of course, the one problem is when the food is taken away from the water, there is negative lift because water is pulling the foot in a negative manner. And of course, lizard has a lot of degree of freedom, and they turn their feet, and they have minimum area and minimum negative lift to maximize average lift force. So one physical constraint about this locomotion is, if your foot speed is not fast enough, the air cavity created by the foot motion will be collapsed, which is negative effect for the negative lift part. That's why by simple math and physics, you see that there's a minimum frequency of rotation, depends on the foot shape and area, and then you need to be higher than that speed. So that's on the order of 5 to 6 hertz for given lizard foot shape. So we looked at that principle and made a robotic version with a given leg using a 4-bar mechanism. So that it's, of course, simplified trajectory than animal with more degrees of freedom. So this is what animal's foot looks like as a trajectory on water. And as you see, the red dots are the part where the drag force is giving you the lift, and the other one is negative lift part, and the other part is in the air. So we did analysis to see which trajectory is optimal for the robot rather than animal. because animal, again, has different objective also. And when we look at our high-performance mechanical design, we'll define the performance as the lift that we can get for a given power input to the robot leg. So that's why we want to maximize that ratio. And we found that this trajectory is more optimal than the biological one. And of course, here, one thing is we are optimizing lift, but of course, also propulsion needs to be optimized in the long run. And that's why animal is also having more tilted trajectory for also more push forward. So the lifts generated during this drag force interaction is, of course, need to be solved numerically. It's not so simple, but of course, the equations are simple. And you integrate under the water the given foot trajectory and speed and the other parameters. One important thing, as we did in the robotic case, is the foot is directionally compliant. Means when it hits the water, it's very stiff. But when it pulls out, because of directional compliance of the joint, it is folded. That minimizes the negative lift effect that I mentioned. Then we started with, of course, the same biomimicry. Like we tried to first make a biped robot, and then we also tried to see if you make a quadruped, even 8 legs. So what's the effect of number of legs? An interesting thing we figured out is going from 2 legs to 4 legs, you gain almost double the lift force for a given leg design, optimal leg design. However, you only need to spend 40% more input power. So in that sense, performance-wise, it's better. If you went 8 legs, interestingly, we didn't improve that much. That's why we stopped at 4. I mean, there are a lot of detailed analysis behind it. I will not have time to get into details, but please ask me if you have questions. Another thing about 4 legs, besides better performance, as we know, is they are better or easier to stabilize than a biped. Because animal, don't forget, has active tail. If you look at the video, they can actively control their tail for a lot of stability function, and a biped robot especially needs to do that kind of very active, complicated tail. So after these initial design considerations, we built this first prototype that uses 2 motors that runs each pair of legs with a trotting gait, because that's the most optimal gait for this kind of speed. It was weight over around 100 grams. And leg speed was on the order of 6 to 10 hertz, which gives a body length speed of 1 meter per second. And lizard is even more than that. And we consumed a lot of power, 6 watt, because of many losses. Indeed, ideally, we were supposed to spend only 1 watt. And performance of the robot for giving lift per input power is 3 times lower than the animal. So this is how it operates on the pool surface. The tether is just for safety. Everything is on board in this prototype, with the battery and everything else. So this is in our botanic garden close to here that you have been, I think, already. So you see that it's not so as elegant as lizard because of the simplified design. It splashes a lot of water, and that's also the same for lizard because in this regime, there is a lot of inertial force that will splash the water. It's stable running, but on the trick you see that we have pontoons. So I'll come to that, but before that, this is more interesting high-speed study, the video study to see how the foot is creating this air cavity, because in an animal we can never see in nature like this kind of real videos. And as you see the foot being directionally compliant, how it folds. So we can see all these details. And in this video, there's just tail, but no pontoon for roll stability. So that proves that this robot can lift on water like the animal, and I think opens a new realm for leg robotic systems, not only operating on ground surfaces, but also on water surfaces. However, that first robot had major issues with roll stability. When there's a disturbance, it was becoming very unstable. That's why we put the pontoons. And if you look at the analysis of that, and this community, you know this very well, frequency of the leg rotation, level underwater, and gait and roll moment of inertia are all major parameters to determine that roll stability. And we changed the design so that we put now every leg an individual motor, and motors are now away from the center of mass. That's why roll moment of inertia is increased, and also robot is now much wider. So that's why it can be now roll stable. And also pitch stability was a major problem if you didn't have the tail. And we analyzed all the nonlinear dynamics here with every foot having different forces. And if you put a passive tail, assuming the water surface is not very disturbing with waves, it will work fine with the right tail. It will be stable. And also, of course, ideally, like the animal, we also explored active tail by putting a motor at the base. So one note I want to give here is, when you look at this lizard, indeed, we are studying at the same time insect flight. And interestingly enough, from the controls and dynamics perspective, these are very similar problems. Because the same thing here, that the wings in this case need to generate a lift and propulsion, and they're highly unstable in it worse than the lizard because their scale is smaller, and plus the pitch and roll, and also yaw now becomes more also important. And right now, these are very initial recent studies of how our insect robot, how it is, in this case, without feedback control, flying. And with all these dynamic problems, we are right now trying to use the similar methods of control and design of the controller and the mechanism at the same time with the same ideas. And even another new direction we are going is now we are using leg robots to jump and then even fly, because when you look at animals, they don't just jump, just don't run or climb. They do multi-locomotion. So they jump, they glide, they perch, they can climb. So that's our long-term vision, and this is a recent robot that can jump and legs turn into wings, which is not published yet, and it can glide passively in this case for reaching unstructured environments in a robust manner. So to conclude, in the leg locomotion systems on water, I tried to show you that you can use hydrodynamic forces to generate lift and propulsion. And in a quadruped design, we try to optimize the leg trajectory and speed and other gait parameters for optimal lift, especially. And I showed you that roll and pitch stability are major issues that you need to be careful about the design. And of course, design is not enough, as we saw in the previous talks, because that's only passive stability. And right now, we are doing active stability control as a new study that, if you're interested, you could see the poster about this new study by my new student, Nitish, working on this project. As another direction in this project right now, the same lizard can run on ground, not only on water. So the basic question is, what about these leg systems not running only on water, but also running on ground and other type of surfaces like sand, and see what type of parameters in the design of the legs in the sense of stiffness and gait and other parameters, plus how about the stiffness should be controlled passively or actively or together. So those are questions that we are studying in collaboration with a biologist and EPFL. So thank you. That's a very good point. As you say, when you go more legs, the major problem is if the spacing between the legs are not far enough, there will be coupling effect because, as you say, the first feet will be disturbing the water surface, and the next one, in that sense, will see a different surface than the initial one. Definitely, there is some disturbance coming from there. That's why the spacing is very important. And if you look at the robot, it has some given length. However, we cannot make it zero. But as you see, it still operates, but there will be some minor loss of lift because of those disturbances coming from the front leg. That's another issue that we didn't add more legs because that will make it even more complicated. So you need to have a very long, like a snake-like robot, basically, which is not so interesting. Yes, please?
So considering that adding 4 legs to your robot doubles the lift you get out of it, I'm wondering why the only example of this in nature is a bipedal lizard, which is normally quadruped. It only becomes a biped when doing running over water.
You know, that's a great question for lizard systems, because if you look at many lizards, especially the ones on the ground, as you say, some of them start with 4 legs when they go slow speed, and then when they go very high speed, they turn into biped. So there are all different optimization things going on. And in the case of, I mean, this lizard also has, of course, 4 legs, but if you look at the functions and plus a lot of other requirements, let's say behavioral-wise, why they do especially this water running is when they see a danger. So they don't do this all the time. So they do this when only they need to go from a river to another side, which is the most optimal, fastest way to get over it, or if there's a snake that they need to escape as emergency behavior. So in that sense, the perception is very important. So when they are biped looking around visually, I think is much easier to detect environment. But from the dynamics perspective, Again, stability-wise, biped is harder, but to reach the higher speed levels, that's an interesting question of which one is better. That's not an easy answer. Assuming you have a great controller that you can stabilize, I think biped, of course, in the sense of energy loss, will be better because you have less, only 2 legs contacting. So, but with the stability issues and all the other issues with these kind of complicated systems, I think 4 legs looks as much optimized. And you still need active tail for control.
I mean, in terrestrial animals, the fastest running animals use 4 legs, right? So.
That's a good point. So, but be careful about the size scale. I think another very important issue about which number of legs is optimal is very scale dependent. I didn't have time to show the scaling analysis of this lizard. The smaller ones are better for the performance and the speed. So in that sense, you don't want this lizard to be very big. The very big ones, at some point, cannot run on water. So it's not so efficient for them. So yeah, that's a great question. So when you get smaller, the stability issues change because of inertial force are much less.
I just wanted to remark that cockroaches also go bipedal when they go fast enough. So they go from the alternator type bipedal to bipedal.
I mean, even if you look at this robot, in the trotting gait, it's basically like a biped in practice, is that right? With a trotting gait, with very high speeds, until some degree, it's kind of almost, in some sense, like a biped. So, and I think the idea is you want to maximize your flight phase rather than ground contact phase, and that's why multi-leg systems, even in small scale, they basically at some point becomes more in the flight mode, and multiple legs become redundant at some point. But I think we should consider that not as only a speed problem, but combine it with a stability problem, performance problem. Because, for example, 8 legs will be more stable, but then the amount of power you need to spend to run with 8 legs gets much, much higher, so that you don't gain much. So I think that's not an easy optimization problem to do.
First,
yeah, so you mentioned this can run on water and on land, and that you wanted to apply it in sand. Could you address some of the challenges of moving on a loose granular substrate like that as opposed to fluid and solid ground?
Yeah. I mean, that's a great question. Of course, what all changes in all of these different surfaces, the interaction forces. An interesting thing with the sand is it has very fluid-like behavior, like the water surface. On the other hand, there are some differences, intricate differences about the shear forces. But otherwise, to me, they are very similar. And if you look at the lizards running on sand, they have similar trajectory and leg dynamics, interestingly. But however, we haven't done enough analysis to say you exact answer about that. I think the more tougher one to us is ground, because that drastically changes the reaction forces that become so huge. But you guys have solved, not solved, but let's say, solving the ground problem. And the problem will be this. So having the same legs can do all these very high ground forces, medium sand forces, and very low water forces. How can you have a system that can handle all of them? From mechanical design, in the sense of compliance, in the sense of leg trajectory and gait, and then control-wise, active stiffness control or passive stiffness control, because with one stiffness, I don't believe we can handle all of the surfaces. That's why the new design has a switching mechanism that when it goes to ground, suddenly we add a spring that a magnetic switch turns the feet, basically triggers a spring, and that way the robot becomes very compliant. On water, you want it maximally stiff, because stiffness, compliance will lose some of the energy. So you don't want compliance on the water surface.
Maybe you can ask the question in
For the bipedal lizard, do you think that aerodynamic lift plays any significant role?
In the lizard? So the lift not, but drag would affect aerodynamic drag. So if you look at the body shape, I'm sure with that high speed, you want to minimize the drag on the body, which we haven't taken into account too much yet. But lift-wise, I can say, yeah, that's negligible. I mean, the air phase is short, and if you look at the area of the foot, the lift generated by that is negligible.
I was just going to say that the difficulty transitioning to water to ground might be a good justification for the forelegs on the lizard, because it needs different stiffnesses in its front legs, different stability requirements on the ground. Just a comment.
Definitely. I mean, ideally what we want is we want a robot that goes to the 2 legs on the ground. And if we could do that, that would be easier for us. But we haven't done that kind of design yet.
So one of the characteristics of animals that are most strikingly diverse is animal size. And that's especially true of terrestrial mammals, which include us. And our largest terrestrial mammal is the elephant, most people are familiar with. Massive, massive animal. The smallest is a shrew, which is about 10 times smaller than a mouse. So it's a very, very small animal. And the difference in size between these two extremes of the terrestrial mammal size are about 1,000,000 times bigger mass than the elephant and about 100 times bigger length. And so this is more about their respective sizes. Now, these differences in sizes create different physical challenges for those different animals. And you can express this in a number of ways, but the way that's said most eloquently, to paraphrase the evolutionary biologist at the sort of around mid-century in the 19th century, is a guy named Jack Haldane. He said, if you drop a mouse down a mine shaft, when he hits the bottom, he might just run away. If you drop a human, they'll break. And if you drop a horse, it splashes. Right? So now those differences in physical challenges are something that the nervous system of an animal needs to deal with. And so one of my interests is in understanding the scaling of sensory motor control. So we have to think about what the performance of the sensory motor system is to understand how it scales. And we think about two main characteristics. The first is what we call responsiveness, which is really how quickly an animal can sense and respond to a stimulus. And you can imagine two different scenarios, a slow one and a high responsiveness one, slow on the left, high on the right. And the differences between these two are just in the speed at which their nerves conduct information. So for those who don't know, your nerves are these nerve fiber bundles. Like your sciatic nerve is a bundle of nerve fibers. Nerve fibers are individual cells, also sometimes called neurons or axons. And those conduct information to and from the periphery. And the speed at which a nerve fiber conducts information is proportional to its diameter, just due to the biophysics of excitable cells. So if you want an animal needs to be more responsive, basically its nerve fibers need to be larger in diameter. Okay? So the high responsive situation needs to have these larger diameter nerve fibers to respond to things more quickly. That's one thing they would need to do differently. But animals might also care about resolution. That is, they might want to have more precise sensing of their environment or of their own body, in which case they would need more nerve fibers to do so. So to have higher sensory resolution, you need more nerve fibers, and that's also true on the motor side. If you want to generate more finely graded forces, you would need a smaller number of muscle fibers per nerve fiber, which would mean you need more nerve fibers for the same number of muscle fibers. And this trade-off exists between these two things. There's a trade-off because in your peripheral nerve, like your sciatic nerve, you could either have a small number of large and fast nerve fibers or a large number, given high resolution, but slow nerve fibers in a given size peripheral nerve. And that trade-off becomes more acute with body size. So let's consider one possibility of the way that might work. So here's a candidate animal that has a very simple nervous system. It has one nerve fiber connecting to its periphery, and we can think about that, its body as being this cube of volume. If you double the size of that animal, and it also doubles the length of the nerve, but if the nerve fiber doubled in diameter at the same time, something we call geometric similarity, then the speed would also double, and you'd be okay. This would be equal responsiveness. But the problem now is you have an 8 times bigger volume, but still only one nerve fiber. So another way this might change is you say, well, let me actually innervate the same volume every time, in which case I'd have to have 8 times the number of nerve fibers. If I put that in the same area, cross-sectional area of nerve, then those nerve fibers would necessarily have to be smaller and slower. So maybe you just grow your nerves. You just have bigger nerve bundles, in which case you could do that. You could preserve your responsiveness and resolution in a bigger animal by making it have a bigger nerve bundle, a bigger nerve. But that only works to a degree, to the point where if you want to get the same responsiveness and resolution, the same performance out of an elephant as you get out of a shrew, its nerve would need to be 50 meters in diameter. Okay? So this scaling has to fail at some point. And the question we have is what gives? Okay? And so it could be that large animals have reduced responsiveness, they have these slower systems. It could be that they have reduced resolution, or it could be both, and we want to find out why. And I should also, which one? I should also just say that there are other ways you can do this, well, maybe things don't scale with volume, they scale with area, maybe you don't care about lengths, you care about the square roots of lengths. But any way, reasonable way you do this, there still ends up being this trade-off with size. that says big animals can't get the performance that small animals can't get in all ways. So let's figure out how we're going to do this. So what we want to do, the first thing we're going to tackle is responsiveness. So we need to be able to measure how quick the nervous systems of these animals are. And so we can set out to measure its conduction velocity. And the way we do that is, in the shrew, we stimulate the nerve at 2 different locations. We measure the evoked potential of the muscle. And then we can measure the time difference in that evoked potential and the distance between the 2 stimulation sites. From there, you can calculate velocity, the conduction velocity of the fastest nerve fibers in that peripheral nerve. And we can do the same thing in an elephant. And we electrically stimulate the elephant nerve. But rather than stimulating in 2 places, we tap its tendon instead. Measure the differences in distance between those 2 sites, the difference in timing, and calculate its conduction velocity. So I'm not going to let you go without seeing what a tendon tap looks like in an elephant.
Let me know when you're ready.
This
I'm
is
ready.
a demonstration
Ready?
of flip
Yeah.
format.
Yes. Oh.
What did she react?
That's fantastic. What happened? That's great. That's good. Perfect. Very good.
Steady.
All right, so you couldn't see it because it happened between frames, but there's an awesome reflex there. That's an instrumented hammer. And this, I should also this is a good time to point out, there's a voice on there you heard, which is Doug Weber, who spoke yesterday, and as well as many other collaborators on these projects that I should acknowledge as well. And you see Dr. Stephen Ong, who's an acupuncturist who does acupuncture on elephants and works with us on this. So what's the result? So what you can do is you can plot mass on the x-axis versus conduction velocity on the y-axis. This is a log-log plot, so you have the full range and sizes over this x-axis. Like the sort of null hypothesis would be that the size of the axons grow at the same size of the nerve fibers in diameter grow at the same rate as the length of the leg. In which case you'd think that large animals have incredibly fast nerve fibers. Measure the shrew, you measure the elephant, it turns out there's really no difference, right? And you can measure everything in between, and this line is basically flat, which says that the maximum speed of the nerve fibers is independent of size, right? So the distance is not, so that means that these delays in the big animals grow at the same rate as their leg length. The delays are huge in the big animals. So they are not as responsive. And you can express this as rather than an absolute time, you can express it as a fraction of something that's meaningful to them, like say their contact, the duration of their contact phase when they're moving quickly. And that's only about, and this is just conduction velocity, that's only about 4% of their contact phase in shrews, and it's about 40% in elephants. So that means just this conduction delay, of which it's just there are other delays as well, that if an elephant were to put its foot in the hole, it's not going to know until 40% of the way, or be able to affect that change 40% of the way into its gait cycle. And it's worse than that because there are many other sources of delays. There's delays in sensing, conduction delays we've talked about. There's a synaptic delay, which involves releasing chemicals across the synaptic junction. Another conduction delay, another synaptic delay, this time we call it the neuromuscular junction delay. You have to then conduct signals along the muscle fibers. You have to then release calcium from where it's stored so that the muscle can be activated. That's called an electromechanical delay. And then you have to generate force. These delays could scale all in different ways with size. We've measured the total loop delay in the components in giraffes in the field in South Africa. And this conduction delay is big, is a big part of it, but only about 40% of the total delay, with electromechanical delay and force generation delay making up the remainder. And so the total loop delay in these big animals is really a large fraction of the contact phase when they're running, making it so that they really only have a hope of affecting their change for perturbation at the beginning in the next stride cycle, right? So the delays are quite long. All right, so that's responsiveness. So now resolution, and I'm not going to give you too much on this, but just to say how we do it. So, the way this works is we harvest nerve fibers, we harvest nerves from a wide size range of animals. We fix them chemically, we stain them, we put them in plastic, we polish them, we stick them in a scanning electron microscope so that we can image them. And then once we have them imaged, we can count the number of nerve fibers and measure their size, right? And then we can test ideas about how those things change as a function of animal size. And just to give you a little bit of preview, this is a sciatic nerve, complete sciatic nerve from a shrew. And don't know if you can see, but these white parts of the myelin sheath that surrounds it, so the inner parts of the cell itself. This is just one fascicle from an elephant of hundreds. So an elephant has a couple 100,000 of these nerve fibers, excuse me, whereas a shrew has much, much less. But I don't know if you can see this, but the size is a little bit bigger in the elephant, but not much bigger. Even though its leg is 100 times longer, the maximum size of the nerve fiber is less than double. And so it's true in other things about animals too, like the red blood cells in elephants aren't any bigger than red blood cells in shrews. And it seems like obviously the legs of elephants are bigger than the legs of shrews, but where it breaks down is at the cellular level, where the nerve fiber, a cell, is about the same size in an elephant as it is in a shrew. So what is the meaning of all this? Well, you got to think about how animals are going to solve this problem. And what I think, so the issue is that they have very delayed sensory information. They probably also have a resolution problem. And so this suggests that big animals would rely more heavily on some sort of prediction to be able to take delayed sensory information and still predict a good motor response that they're only going to be able to invoke in the future. And we know that humans do this, right? Tons of studies about that. My small addition would be this is why. This is a factor of our size. And when you think about it, humans are actually a relatively big terrestrial mammal. We're some of the biggest. Right? Thank you.
Do elephants trip ever?
Yeah.
Do they trip more often than smaller animals?
I don't know. I'd say probably not. Yeah, and so there's, so one way you can deal with time delays is the one I just mentioned, which is sort of interesting from one standpoint. But another thing you can do is behavioral things, right? So elephants will avoid slopes. They will avoid slippery things that they perceive to be slippery. So they'll do a whole bunch of behavioral modifications to avoid the possibility, not put themselves in circumstances that shrews would. But often we start to talk about what elephants do, but I guess I do want to sort of amplify that we are close to what elephants are in terms of size. And so, we do embrace, I think, similar control strategies, which are a factor of our size that say really small animals like shrew and mice wouldn't be.
So you mentioned this nerve delay being a huge factor in stabilizing gait. Could you comment maybe on how functional muscle architecture might play a role in negating that gait, or negating those delays, or potentially providing a less dependent on neural control mechanism for potentially stabilizing gait? Because obviously there are morphological differences between these animals.
Yeah, there are. There's two things. So, so certainly another good strategy to ameliorate any effects of delays would be some sort of preflexive control, right? So that you can passively and rapidly reject perturbations as they're presented. And so I would think that the bigger the animal, the more likely they would be to embrace those sort of strategies as well. And then the second thing is there are obviously big morphological differences. It depends how you look at it too. So elephants are quite out there, but if you remove elephants from the picture, things scale really well with geometric similarities, which means that if you were to measure the leg lengths of animals ranging in size from shrews up to basically like horses, it scales with length proportional to mass to the 1/3, which is what you'd predict if you just were to sort of zoom in on a shrew. And so I think we're tuned in to visually see big differences morphologically, but there's a lot that's similar as well.
John? How much of this do you think is sort of about evolutionary prey versus predator relationships? Because a shrew has to be worried about being preyed upon by maybe a small predatory bird, and if the bird is smaller, then it'll have really good reflexes and responsiveness, and so the shrew sort of requires that as well. So the elephant has gotten so big to the point that it does not have to worry about very small predators, so it seems like anywhere along that spectrum, the size of the animal that you're looking at has to either prey or worried about being being preyed upon animals of a similar size. So it seems like if the elephant is willing to be sort of conservative in the way that it walks, as you say, it avoids slopes and all that stuff, then it just simply does not require the responsiveness that a shrew requires because the shrew is being preyed upon by faster things.
Yeah, I see what you're saying. There are, so we think about that, but then we also think about the fact that there are other things that you have to deal with, right? Like putting your foot in a hole isn't a predator-prey interaction, but is something that you would presumably like to reject right away, right?
And then realize that it's terrible at dealing with holes, and then it won't gallop across areas that it can't see the ground well on.
Yeah, so those are behavioral modifications I mentioned. And then there are other things where we think about when sort of absolute delays might matter, or absolute resolution. So it could be that a disease-borne, carrying mosquito is just as dangerous to an elephant as it is to a shrew. And in which case you would want to respond to that mosquito at its frequency, and you'd want to have very tight resolution so that you can hit it as well. So like I do see what you're saying, and whenever we break this down, it's sort of like, yeah, it could be that, it could be this, and it's hard to know. That's where the experiments come in. The experiments say, these things are pretty slow for these big animals, even at the speeds at which they move their limbs, such that and elephants do move quickly in some circumstances, and presumably it's not just over tracks with terrain they can totally count on. In which case, if they do get perturbed, it's going to take them a large fraction of their gait cycle to recover, to even know that it's happening. Yeah.
In these sayings, have you looked at the difference between animals and myelin, and say, like, the proportional thickness of myelin?
Yeah. We don't think so, but that's because there's some really good work on this that shows that the optimal myelin thickness is about 30% of the total diameter of the myelin plus cell, so that you get 30% myelin and 70% cell, and that optimizes the speed of the conduction, and so there's no reason. I mean, that's sort of something that animals can change independent of the size. So you'd expect all animals, I think, to try and optimize that, right? And even small animals, and it looks like that's the case across everything we see. Is that ratio is pretty much preserved.
So last night at the museum, they showed us a model of the T-Rex brain that suggested that it was more of a scavenger than a predator, like I saw in Jurassic Park. And so now the T-Rex in Jurassic Park is even further off the mark because it's now a slow and clumsy scavenger. Is that about right?
Well, yeah, but I think I wouldn't claim I'm responsible for that conclusion, because people have shown that in many ways, that it's unlikely that those big animals ever moved quickly. And there's trackway evidence to that. There's issues with supporting the weights, the loads that moving fast brings. There's our problem. So there's evidence from multiple directions that suggests that those big extinct animals did not move quickly.
So I want to make a provocative statement based on your results, which is that...
Well, should I preface this by saying, I don't know if you noticed my title, but it's half of what's written in the thing. And so half of my title, what I submitted, the title in the program is something about why robot control is...
Motor control delays make robot control strategy irrelevant to biology.
Right. So that was not the title I submitted, and I think the author of most of my title is about to ask a question. There you go.
So I think everybody in this room accepts that large animals are way, way better at locomotion than our best walking robots. But that's despite the fact that our robots have much, much faster bandwidth, basically, in both sensing and in actuation. And so our robot control strategies are even worse than is evident by the bad performance of our robots. They aren't dealing with this problem that's fundamental to large animals.
Okay, so in human walking, our ankle joint produces bursts of positive work during leg stance. And here's one example of our ankle power reported by the Bergman. So the gray area is the intact, healthy subject walking. So you can see during this period, our ankle produces a peak power to push off. And for patients with some gait pathology, such like patient recover from the stroke, they may have less push-off during this phase. So these two curves is one example of those patients. And this patient also has more higher energetic cost than the healthy subject. So it seems like there's some relationship between less push-off and the greater energetic cost. However, so the most patient has not just less push-off. They also have some other disability like less muscle force or instability in walking, which also costs more energy. So it's hard to say what's the relationship between the less push-off and the greater energetic cost. So in this research, we are going to study the relationship between the less push-off and the energetic cost. So we started from the inverted pendulum model. So in this model, we can apply impulsive push-off before your leading leg touches the ground. And then when your leading leg touches the ground, there is an impulsive collision, which dissipates energy. And if you choose a proper push-off, you can make the model work in the limit cycle. And if we have less push-off in the model, we will have greater collision, which dissipates more energy, and require this model to perform more positive work during the stance phase. Therefore, we hypothesize less push-off leads to greater collision, and then require your joint, your limbs to do more positive work, which should cost you more energy. So to test this hypothesis, we recruit a healthy subject so that they have any problem with walking. And we ask them to wear this ankle prosthesis, and we use a steel cable to constrain your plantarflexion motion. And by applying different lengths of the cable, we can reduce your plantarflexion more. So we have 5 different conditions. The first one is working with an ankle prosthesis with no string so that your ankle can plantarflex as much as you can. And then we have 4 different lengths. For the shortest cable, we can reduce your plantarflexion up to 25 degrees. So we ask the subject to wear the ankle prosthesis working on the treadmill with a constant speed. So we expect when we have shorter cable, we will constrain more your ankle motion, which leads to less push-off. And then the less push-off causes greater collision and require you to do more positive work, and then which should come with higher metabolic rate. So here's our result. First, we can look at the ankle angle. So this one is a normal walking without ankle prosthesis. And the upper direction is plantarflexion, and it's start from heel strike to another heel strike. So in the end of the stance phase, you can see our ankle angle plantarflex, and then produce a positive power to push off. When we applied more and more constraint, shorter cable on the ankle prosthesis, you can see we reduce the plantarflexion angle more and more. So we check the first one. So the next thing we expect is that the more constraint should lead to less push-off and cause greater collision. And to quantify this, we measure the center of mass work rate, which is defined as the dot product of ground reaction force and the center of mass velocity. So this curve is one example, start from heel strike to toe off. So after the heel strike, we have a negative center of mass work rate, which means your leg is doing negative work on your center of mass. And then we have this rebound phase when the leg is doing positive work on your center of mass. And then negative we call preload, and positive for push-off. So we can integrate the curve to get the center mass work for individual things. So we look at the push-off first. Here is the result for constraint case. So you can see when we have more constraint, our push-off decreased. So we check this. And for your information, when we have a maximum constraint, we can reduce the push-off up to 40%. The next part, we look at the collision. When we have less push-off, we have more collision. And the collision increased about 20% compared to no constraint case. And then during rebound phase, our limb doing more positive work. So which we check this. So now we know during the same phase, our limb doing some more positive work to compensate the collision. But what we don't know is which joint contribute this work. So to know that, we go to individual joint. So we look at the ankle joint first. This was the ankle joint power over gait cycle. We found that when we have more constraint, our peak power decreased. And to quantify this, we can integrate the joint power to get the joint work. So the red bars are positive joint work, and the blue bars are negative joint work. So we found that when we have more constraint, our positive ankle joint work decreased, which corresponds to the decrease of the push-off. And then we can look at the knee joint. So after heel strike, our knee joint perform negative work. And when we have more constraint, the negative work increase, which corresponds to the increase of collision. And then during this phase, our knee joint produce more work, which corresponds to the rebound phase. So to quantify that, we also calculate the knee work over a strike. So when we have more constraint, we will have more knee negative work correspond to your collision phase, and more positive work corresponds to your rebound phase. And for your information, we also look at the hip joint, but we didn't observe any significant change in the hip work over all the constraints. So we can sum up all this work to get the total positive joint work and the total negative joint work. We found that when we have more constraint, the total positive work increased. And it increased about 60% compared to no constraint case. So this increase of the total joint work should lead to higher metabolic rate, which is our last expectation. And yes, we found that when we have more constraint, our net metabolic rate increased. And it increased about 30% compared to no constraint case. So therefore, this is our take-home message. So less push-off leads to greater collision, and then the knee perform more positive work to compensate the collision. And then it ends up the net metabolic rate increase when we have more constraint and correlated to the total positive work. And here's a question for people doing robotics. So in this study, we show that the ankle push-off is important for the energetic cost of human walking. But what if about the bipedal robot? Can we use the ankle push-off to increase the efficiency of bipedal robot? So that's a question for you guys. And thanks for your attention.
You're swimming in time. Robert?
Thank you. Nice work. Thank you. So I have a question. From one of your images of the apparatus, it looks like there was some sort of rocker foot that the subject was wearing. Is that right?
Well, when we bought the ankle for that, there's a rock, and we try to remove that, but that still have a little bit. And we found that if you don't really have any curve, that's really hard to walk. So we didn't intend to have that curve, but it's still there.
The only reason I ask is because Andy Hansen showed that if you wear different curved rocker shoes, that you adapt the ankle to maintain an invariant roller shape. And so I'm wondering if that could have that adaptation might have some influence on your results. That's my question.
Okay, so the thing is, for all the constraints, they all have the similar curve. So yeah, I agree. The curve should change your gait a little bit and maybe reduce your push-off rotation in some degree. But we kind of constrain life among all the cases. So I think it will not change the result of this study. But that may change the magnitude of all the measurements.
How did your subjects modify their ankle kinetics and kinematics? It looked like they were going into a little bit more mid-stance dorsiflexion in preparation when the constraint was imposed. Did they also increase their ankle joint plantarflexion moments?
The ankle plantarflexion moment increased a little bit, and I would not say that's significant. So the most of the change in the ankle is the range of motion and the power. So we tried, at the beginning, we were thinking about using a spring to reduce the power, but it ends up a little bit hard to decouple your motion and your moment. So in this case, the moment didn't change a lot. So, but that decreased a little bit. I didn't do any statistic tests on that, but that's what I observed.
Did the stance deflection change with constraint? Scott Delp said last night that reduced plantarflexion was one cause of crouch gait. So I'm wondering, as you increase your constraint, did you get greater stance deflection?
Yes. Yes, the knee joint, the angle of knee joint changed, and I can recall that the knee flexing moment is higher than others. Yeah.
So because you have limited the ankle extension at push-off was less. So now if the subject wears a high heel shoe, then the ankle has already extended. But then because of the high heel shoe, you have a longer leg. So your step length will be smaller, or the heel stress will be less. So if you try the same experiment with high heel shoe, would the cost of transport be less than this case? Or?
Okay, I think that's a good idea, but I didn't wear high heel, so it's hard to imagine what will change in the gait. And when I observe some people wear high heel, I think their gait is quite different from normal walking. So yeah, I think that would be interesting, but so far I cannot really imagine what would I change the whole gait.
More questions? Yes. Okay, so this is one way to restrict ankle plantarflexion by restricting the peak angle. Did you think about or play with and pilot test with other ways to make ankle push-off less effective, like a damper on the ankle joint or a spring that fights the muscles?
Okay, so we haven't tried a damp, but we tried some springs, and we have some difficulty to find a good stiffness because different subjects may have different preference. And also, when we try some really stiff spring, that just ends up like a steel cable. So we tried that before, but we didn't really got a good number of spring. And then for this study, we just try this. And in the future, maybe we can try to think about, yeah, some other way. But the problem is that the moment and the motion is kind of coupled together, and it's really hard to decouple them.
Just a comment. I think I can give you a thesis where there's a partial answer to the question that you asked.
Okay.
What is it? Is it yes? You can, for the same amount of energy, you can walk faster using ankle push-off. It depends on how you penalize that impulsive, how you count the energy in that impulsive push-off.
Well, I think the question is not just is it a good idea, because we certainly think it's a good idea to push off the ankle, but it's more of a practical issue with robots because you have to get the power down there somehow, and you either need to put an actuator there, or you try to have an actuator up by the hip and then transfer the energy down. So I think it's really about the practical trade-offs. Everyone probably could benefit from being able to push off,
But is it worth it given the design constraints and, you know, realities of motors and cables and things like that?
Well, that's what Peter's working on, isn't it? Giving us a passive mechanism for more push-off.
I think you're, not necessarily Peter, but Peter and other people, yes.
Yeah.
Maybe Steve has a comment on, for robots, whether you, if you were to build another robot, would you try to get push-off?
I think that I'll wait until Josh Caputo talks about, he has something that directly addresses this one.
So, how do you think the working cost of heaven on the push-off? So there's a little bit of push-off go a long way. I mean, so let's say you had some problem with one of your legs, right? Like, do you benefit? Do you get 80% of the way there in terms of the and work and metabolic cost savings with a 20% push-off? Compared to the optimal.
So the relationship, well, the mathematical relationship between the cost and the push-off is still unclear. So the number I give you is just the way I deal with the data. But the real relationship is, I think it's a little bit hard to say because there's a baseline for individual subject. So everyone has a little bit different. So I cannot give you a number about how much push-off will lead to.
You know, address it more from the modeling point of view without the subjects, right? Just how it seems to be like a little bit of push-off gets you a long way. You don't need to get to the so if you reduce it by a little bit, you might expect small changes.
Yeah. So you mean if we have reduced push-off, in the model, how much energy, more work is needed for that? I don't have a number there, but from the configuration of the model, you will need more work. That's the only thing I can say now. Okay.
So maybe while the next speaker sets up, I can ask the last question. So it feels like you're making an argument about the consequence of restraining the ankle range of motion by using a work argument. You're saying that restricting range of motion reduces the amount of work available, but it's not clear that it reduces the amount of work that the ankle is able to do. The ankle could produce a much higher force or smaller range of motion. In principle, you could get the same push-off. And it feels to me that the person is choosing not to do that intentionally when the angle of range of motion is restricted because perhaps applying higher forces is bad because of a different reason.
Okay.
So it feels like there is a trade-off between force and work that's playing a role here that's affecting your result. That's my sense. Can you comment on that?
Yeah, so I think one thing about the joint moment is that the joint moment is just kind of, you can think about that as the central pressure under your foot. So if the subject is walking in the same speed with the same step length, so you can think because they have the same mass, so the central pressure will not change too much. In that case, the moment cannot be changed too much. Yeah, so, and again, there's still, I said that before, so it's really hard to decouple those things. So now we just constrain your range of motion, but it ends up the moment didn't increase. And I think that's the fundamental thing in the dynamics.
Thanks. I'm going to present a study that shows that a simple
plantarflexion assisting exoskeleton can reduce metabolic cost of walking. So we all know that humans are good bipedal walkers. We have a low net metabolic cost, which is due to the fact that we move as an inverted pendulum, which allows interchange between potential and kinetic energy. Still, walking has a net cost of around 3 watts per kilogram. That's perhaps a little bit difficult to imagine what that really means. So I came up with this comparison with your breakfast which you had a few hours ago. Walking requires around half a bagel per hour. So there are some companies that are building devices to make walking even easier. Some of these are aimed for able-bodied subjects. Others are designed for people with impairments. As you can see, the technological improvements are really impressive. Unfortunately, there are only very limited scientific publications about these devices. So, for example, I don't know what's the effect on metabolic cost. On the other hand, there are a lot of publications with simpler devices that assist plantarflexions. However, until now, none of these was able to reduce metabolic cost below the level of walking with normal shoes. Also, a reason for this could be that there's still insufficient knowledge about the interaction with the human user. For example, it was not yet known what would be the optimal actuation timing. So this brings me to the aim of our study, which was to find out if it's possible to further reduce metabolic costs by studying the effect of actuation timing. In order to do this, we used this bilateral ankle-foot exoskeleton. As you can see, plantarflexion is assisted by means of these pneumatic artificial muscles which are mounted on the rear. Metabolic cost was measured with spirometry. The pneumatic muscles could be activated at different timings of the gait cycle. So, for example, in one condition, we had them activate from very early until 2 off. 100% is one stride. In other conditions, the activation started at different times in the gait cycle. And subjects also walked in an unpowered condition and a condition with normal shoes. In the mid-stance phase, we know that there's little concentric muscle work, so there we expected to find little metabolic reduction just because there's not much to be gained. During push-off, however, we know that the ankle needs high concentric muscle work in order to push the center of mass into the next pendulum. So here we expected to find high reductions. And our results confirm this hypothesis. So in this figure, you see net metabolic cost expressed as a percentage of the net metabolic cost in the unpowered condition. A large negative bar means a high reduction. The actuation timings in the different conditions are still shown on the horizontal axis with corresponding colors. So we see this U-shaped pattern with the highest reduction in the last condition with onset just before opposite leg heel contact. Opposite leg heel contact is at 50%. This corresponds to a simulation study of an elastic AFO, which shows that the stiffness of the AFO is optimal when it allows plantarflexion to start just before opposite leg heel contact. And when we compare the reduction in the optimal condition versus walking with normal shoes, we find a significant reduction of 6%. As far as we know, this has not yet been shown in able-bodied subjects. In order to find an explanation, we looked at the center of mass kinematics, and when we zoom in on the step-to-step transition, we see that there's a correlation of the amount of drop of the center of mass after heel contact with metabolic cost. So the optimal
reduction in this condition can be explained because the center of mass is more effectively being redirected with this timing, which is some kind of experimental validation of the paper of Kuhl. I'm going to end with some conclusions and perspectives. So if we do a curve fit to our results in different conditions, we see that the highest metabolic reduction could be expected with an onset at 37% of the stride cycle. This would be useful for devices where available energy is not an issue, such as opposite leg heel strike is at 50%. So you always have to think that you have two legs. This figure shows the shows one assisted leg, but at the same time the other leg is also being assisted, which is maybe more clearly shown in this figure. Now, some of you probably have been wondering about the fact that the total actuation duration is not equal in the different conditions. So in order to take this into account, we calculated the performance index proposed by Sawicki, which is a ratio versus mechanical work in the different conditions. And when we do a curve fit through this one, the optimum is a little bit later, more or less at 45% of the stride cycle. This timing could be useful for ambulant exoskeletons where efficient use of available energy is, of course, critical. As a brief intermezzo, I can mention that we are now going to look how this translates to timing of robotic prostheses. For this, I will use the device of the next speaker. Now back to exoskeletons. The main limitation of our device is, of course, that it's not portable due to the source of compressed air, which is not portable. A solution that has often been suggested would be to recycle negative work that happens during the gait cycle. There's one limitation which we believe that was briefly mentioned in a paper from Lee and Donelan, which says that for harvesting eccentric work, you should rather not use work that is used for stretching and shortening of biological tendons, because you don't want to take energy away from this already efficient biological mechanism. But I've had some discussion with Sawicki about that, so I'm not entirely sure if that's really applicable for recycling exoskeletons. Still, we took this into account. We measured inverse dynamics of the knee, and we see that during this phase, which is at the end of the swing, there's a work burst which is high enough in order to theoretically power our exoskeleton, and the figure shows a purely hypothetical mechanism that could maybe one day realize this. I'm going to end my presentation with a statement of Daniel Ferris. He predicts that by 2024, exoskeletons would appear in the streets. When I first read this seemed totally science fiction, also based on Lucas et al. However, when I think back about the impressive commercial exoskeletons which I have shown in the beginning, then maybe it's not so unrealistic. Maybe all these devices need is some slight optimization based on studies like the ones that are presented at this conference in order to become really successful. This concludes my presentation. Thanks for your attention. Feel free to ask questions.
Just a technical question about what you mean by timing. Is that timing of onset of, the valve releasing the air, or is this the onset of force? Or?
It's the onset of force, here I have the moments in the different conditions. Yeah, the timing was controlled with foot switches with a feed-forward algorithm. So we predicted when we had to open the valve in order to obtain a certain timing. This was more or less accurate. The timings which you see in the results graphs, they are really measured timings. So those are actually the timings when these moments pass a certain threshold. So these are actual timings. Of course, the actuation is not instantaneous.
Just curious, you played with optimizing the timing of adding additional power, but what about the magnitude of power that you add? Is there
yeah, as you probably know, with these metabolic experiments, you don't get your data instantaneously like in a simulation. So there were a lot of things which we just chose by trial and error. I think certainly in prostheses, Josh will have a lot to tell about the amount of force. So what we did was just simply set a fixed air pressure of 3.5 bars, and yeah, when the actuation was meant to start, we just completely opened the valves. Force increases somewhat gradually because the pneumatic muscles don't fill instantaneously, but yeah, we didn't control force at all.
Yeah. Okay. Just to make sure I understand it. So did you compare the amount of energy you put in from the muscle versus the improvement in metabolic cost?
Yeah, that's.
And you took for this one, you took the approximation from force times velocity from the muscle, or where did you put that from the pneumatic one, or where did you take it exactly from?
We measured the force with a load cell, and we measured the ankle angular velocity with 2D video kinematics. We multiplied both so that you obtain power, and then integrate it, and that gives you the amount of work. And in the ratio, there's also this ratio of 25, which makes it that it's more a relevant number. So a number of 1 would mean that the exoskeleton completely restitutes biological work. So that's how we obtained the ratio. Is that an answer to your question?
Absolutely. And a short second question. Did you check against any other model ideas? So here you say you propel the center of mass upwards. There's other theories saying the ankle power goes into swinging the leg, for example. Did you check against this type of hypothesis?
Yeah, there's a lot of other explanations which are in the paper. I think another explanation is just very simply, if you look at the resulting power in the different conditions. So these are exoskeleton power profiles, and you compare them versus the biological power, which is shown in the black line or less. Then you see that the green line, the timing corresponds very well to the biological one. What you say about the swing leg is also interesting. We also measured EMG in different experiments. This is not in the paper, but what you see, the colors are a little bit different, but the light blue one is the metabolically optimal condition. What you see is that the exoskeleton produces a little bit reduction in the plantar flexors, but maybe not so much compared to some other devices like the ones from the group of Ferris and Sawicki. But surprisingly, the exoskeleton produces higher reductions in the vastus lateralis, for example, or the biceps femoris is also maybe a little bit surprising. So it seems like it doesn't so much really directly assist the plantar flexors, but also assists like the more general kinematics, like launching the swing leg. That's also really the perception that subjects have, like their swing leg is being propelled forward. I don't know if that's a good answer, Andy.
Can you be more clear? You said you had the 6% number up there. And you said as far as you know, this is not seen before. What is your claim about what was done that was not done before? Just say it more precisely.
Yep. The group of Sawicki, they did find a reduction versus normal shoes, but that was in walking with an imposed longer step length. So in normal walking, we didn't find that yet. Bregman, who did the simulation of the elastic AFO, there's a paper where they find a significant reduction in impaired subjects. Of course, those start with an initial impairment, so I can expect that in those it must be easier to have something to optimize. In able-bodied subjects with a powered AFO, of course, there are other transportation devices which are successful, but with powered AFOs, as far as I know, nothing like has been published. I have here on my landscapes indicated with those triangle and circle symbols the data of similar devices, and it seems like we.
Can I say it in a more dramatic way? Until this paper, there had never been a device where if you walk, you just walk, we measure energy cost. Then we give you the thing to wear and measure your energy cost again. The result was a reduction. This is the first time that with really selected legged locomotion in humans, or human locomotion, you give somebody a device and their energy cost is reduced.
Yeah.
So this is the so-called normal barrier of human walking.
The what barrier?
The normal barrier. Beating normal has been one of the little goals in the community for 5 to 10 years, and finally we have done it. Now there are lots of little details of like thresholds of what would be the ideal thing would be to break with a totally autonomous device or one that has no external energy input. But even with all the energy input in the world in a lab setting, it's ever done. So,
do you agree with that?
Yeah, as far as things are published, yeah, I totally agree. Well, the Hulk, for example, they make these more commercial statements, like you can walk with 100 kilograms, and I don't know, I would like to hear from those people, but it seems like a more clumsy device. I'm quite skeptical. I don't know. I can imagine those guys have more.
Can I
yeah.
add to what Steve said?
Yeah.
Which is that there's been several papers where people say they have prosthetic devices which make it easier to walk, but they all do what I would call Enron accounting, which they do some subtracting of something or other. So they say it's easier to walk with this device, and then the second part is turned on than it is when the device is on you but turned off. And then so they do some subtracting of how hard it is to wear the device. So think it is a big new thing that you can wear something which makes it easier to walk. It's sort of surprising given all the hype in the past that it really hasn't been done before.
Yeah.
So I think you should
I think so.
Maybe
Okay.
you can have one listener next week when it checks out.
Yeah. There's been a study from, I think, Grabowski, which I don't know what it really is, but it seems like some old version of the Hulk. It seems like some preliminary work. Yeah, and as far as I know, those devices, they go from an increase in metabolic cost versus non-wearing between 10 to 60%. 60, so, yeah. 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 That's true. Yeah. Thanks. Thanks.
So I hope you're excited about push-off. There's been lots of talk about it. I'm going to say a little bit more in the context of lower limb prostheses. So the biome has demonstrated to all of us that powered ankle-foot prostheses can increase preferred walking speed and reduce metabolic rate for people wearing conventional devices. There's a picture of it there. It achieves this using a biologically inspired controller which generates positive ankle push-off work comparable to that of the normal human ankle. This is a great result, and it shows that robotic devices can really make a difference for amputees. But I wonder, can these improvements be furthered? Perhaps device work which provides maximal benefit to the user differs from that of the biological ankle. I want to identify what level of push-off makes sense for these devices by systematically varying the push-off and measuring users' response. We hope that identifying relationships like these will inform the design of future prosthetic devices. So we systematically varied ankle push-off work using a test bed that we developed. You can see it over here. It features a 1 degree of freedom torque-controlled joint, photograph of it there. It's powered by a Bowden cable tether, powered through a Bowden cable tether by an electric motor. And there's lots of details about this. Ask me later if you're interested. So then we measured the response of 10 able-bodied subjects walking on a treadmill at 1.25 meters per second. Okay, so what do I mean by ankle push-off? If you look at the healthy ankles torque, laser pointer's not working. Oh, there it goes. Torque versus angle, you see this clockwise loop here. The area inside this loop in healthy subjects at 1.25 meters per second is positive. It's about the area inside is positive. It's about 0.12 joules per kilogram. That's what we call push-off. So for control, we do a linear piecewise fit of this. And this is our nominal behavior that we do torque control on. So we then increase push-off work from 1 to 4 times approximately 4 times the net work of the healthy ankle. And we're also interested in what happens when you reduce push-off. So we vary from normal down to -1 times normal push-off. So we propose that the more the merrier in terms of ankle push-off work. This comes from the idea that 1 joule of muscle work costs you 4 joules of metabolic energy. So if you can effectively replace each joule of muscle work with a joule of robot work, you save 4 joules of metabolic energy. We expect diminishing returns as this becomes difficult, as it becomes difficult to effectively replace muscle work. And perhaps for crazy amounts of push-off work, you could incur an additional energy cost at cost of 0.25 joules per kilogram as your muscles absorb the added energy. So I'm going to show you my results in a series of plots with these axes. On the horizontal axis, we have net prosthesis power, which is the average per step work divided by the average stride time and body mass. This gives you watts per kilogram. And on the vertical axis, we have net metabolic rate, which is the amount of energy used in each condition, subtracted by the energy used for 0 work, and we divide that by body mass. So both axes have units of watts per kilogram. So here's the data for our 10 subjects. And the relationship that we expect if muscle work replaces, or robot work replaces muscle work 1-to-1, the slope of -4. We estimate, or we fit our data with an exponential curve, and we see, laser pointer's finicky, in this range, we're close to that -4 slope, and then as you get into really big levels of push-off work, the data starts to fan out, and you see diminishing returns. So you see some inter-subject variability here, and we wonder, on one hand, maybe the subjects need more than 3 days of training to get used to this crazy amount of work, something like 4 times normal. But it also could be that subjects are just different. Every one of us has a different energy trade-off in this paradigm. So you see some subjects, yeah, it's hard to see. Anyway, some subjects get close to this -4 line and they maintain that throughout the range, while others show a more bowl shape with a minima. Anyway, a small pitch for the test bed is that this is a great tool for figuring out what particular individual subjects' needs are when you're fitting them with a robotic device. So in conclusion, we see a 15% reduction in energy use with levels of push-off work 400% of that of the human ankle. And metabolic rate is continuing to decrease at this point. This suggests that we should design assistive devices that produce as much ankle push-off work as possible. Currently available robotic prostheses add an approximately 1 kilogram mass penalty at the ankle for every 0.15 watts of device work. If you add this based on our knowledge of how mass affects energy use, it drastically changes the cost landscape. Of course, some mass is required to provide ankle push-off work, but we believe future devices could approach these reductions that we're seeing through further mass optimization, perhaps through energy recycling of otherwise dissipated negative work, and certainly by offsetting actuation mass from the ankles to the hips. Finally, we now have a quantitative assessment of the effect of device push-off work on metabolic cost, and we can predict the response of users to candidate device designs. Thanks. I guess Manoj picks.
Yeah. So kind of a practical question here. I really like your idea of supplying this ankle push-off. I think it's great. But one of the things you need to consider when thinking about someone wearing a prosthetic is you're transmitting a lot of energy into what's effectively soft tissue. So there's issues of bruising, and there's issues also of energy dissipation. So could you comment on how you might balance this high energy input with things like, say, potential pain for the user?
Interesting. Sure. So clearly this isn't addressed here as we're testing on able-bodied subjects, and we hope to get into the amputee community next. The interaction forces with the person are not necessarily bigger if you increase the amount of push-off work, but I don't have anything specific to say on that. Both of you at once.
So do you notice, like, are you able to see? You mentioned you trained for 3 days, and who's that like, really low data points that you would see?
No, and that's interesting. So we chose 3 days because it seemed like a good number of days from our pilot studies. The first day, especially the first condition that the person ever walks on the device, they have a lot of trouble. But by the second condition, and certainly by the second day, they're very well adapted. And we said, let's do the third day so we can see some consistency between day 2 and 3. So it seems like a lot of training, but I'm not sure. The really low subject was someone who I thought would never learn how to use the device. And eventually they did, and they showed really low energy use. So yeah, you want to see the data. I just realized all of my figures are missing a data point. So I need to go back a little. Oh, no, it's there. You just can't see it. Right here is the subject I was talking about. Yeah.
But so you're not, like, so there's this, like, rapid adaptation thing, a couple days is fine, but they could be learning over a much longer time scale too, right?
Yeah, it could be. And it could be that they require some coaching. Yeah.
You're not seeing anything, maybe you have looked at what's like from day 2 to day 3, where you should be.
I haven't noticed much difference in day 2 to day 3, either in metabolic rate or the amount of work that they're receiving or anything really.
I'm just wondering about this factor of 4 as your theoretical fit. So I understand the factor 4 in terms of muscle efficiency, but not all work is created equal in the walking cycle. So the reason we're in the push-off dance club is because we think that work in the push-off actually gives you more energy benefit than the work itself.
Yes.
And so it should be much more than a factor of 4 as a theoretical gain, not just a factor of 4.
Could be.
So why do you pick a factor of 4 as your theoretical target?
I think it's a conservative landmark. And certainly it doesn't appear to be crazy in relationship to the data. But you do see subjects that are on the other side of this line. That's interesting.
How do you choose the alignment of the prosthesis for the subject? Is it possible that there's interaction between this metabolic rate and adjusting maybe the AP alignment?
Definitely. There's a lot of choices we made in the design, in the fitting, everything, that we just sort of made our best attempt. And we didn't optimize them. We keep them constant across all subjects. So all subjects wore the same simulator boot with the same alignment. So there is an AP offset, and it's constant across subjects. So I expect if you spent more time optimizing the system, you could get much bigger reductions.
Is there any correlation with subject height or foot length with these data?
I haven't noticed anything yet. So certainly we're optimizing, we're normalizing by body mass.
Art and then art. So some of the experience we've had in the past, especially with Steve and others putting stuff on people's feet, is
we would design something that would provide assistance. Try out our wonderful device that assists you, and then the person would put it on, and then they would say, get this thing off of me. And so we sort of have this informal theory that you don't want to force the person to deal with sort of unexpected or just things that are not under their control. And I'm sure you guys have thought about this. So right here, you're controlling this based on phase and gait. But you probably also considered other variables that would be slave to something that a person has more active control over. Because phase and gait, you sort of, it's better than time, but also you don't really have a way to modulate that very easily while you're walking.
Yeah, that's true. We wanted, well, first and foremost, we wanted something where we could conveniently and reliably control ankle work. So we didn't want the person to have much choice over that, of course. To answer your question, I mean, an equally subjective response would be that subjects don't seem to reject it. Certainly by the third day, they get pretty comfortable with it. And we quickly piloted a thing where we asked them to rate different conditions on a scale of 1 to 10. And it was interesting because people could really tell the difference between conditions and had a clear preference.
Can I just add something quickly? I think actually what people want is something that is easy to understand. And in our other experiments with the exoskeleton, slaving something to time works great. People love it. So it's just that sort of supersedes these other things, even though in a lot of our models we think putting things in function of time is a bad control. Remember, it just makes it accessible to learn.
Yeah.
So I was wondering, as you increase the amount of work that you're applying, were there any signs of overcompensation on the other leg that the person putting out more work on the left leg that's offsetting the work saved on the right, where
Yeah.
it might be viable or valuable for you to choose
Oh, I see. Well, I'll answer the first part first. Probably, and the answer is probably in the inverse dynamics analysis that I have yet to do. So we captured force plate data in motion capture. And, I'm really interested to see how all these other factors are changing as we change push-off work. As to bilateral, I mean, sure, bilateral would make a lot of things different, interesting, maybe easier, but we've just stuck with this because it's simple and definitely relevant. There's a lot of asymmetric amputees.
I'm kind of surprised to see that as you put more and more power into this prosthesis, you don't see net metabolic rate coming back up as the subject makes adaptations to kind of absorb that energy. So kind of on the same basis as the last question, I was wondering if you had any type of analysis to show the joint torques that maybe the knee or the hip, and if that, or if you maybe didn't approach the amount of power that would require the kind of gait adaptation.
Right. Well, as I said, that's in progress. I invite you to come down and take a ride and see what you think. It seems to depend on the subject. So you may be able to pick this out, but there's a blue subject here that comes down and it has an increase. And that was consistent for them. Other subjects, they just go straight down. We never even get into the range of diminishing returns. So something interesting going on there. Yeah, indirect respirometry, Oxyconn. Roughly. Measured. Yes. I want to. Certainly, this begs the question of what happens if we keep going. At this point, we can't go higher just because of limitations of the hardware.
I have a quick question. Did the people that had a greater reduction in metabolic cost also feel better, essentially? You said you had informal interviews.
Yeah, we just piloted it. I didn't do a consistent job of that, so I can't tell you.
What do you think about what
I'll come back to the one subject who you see with this really low point. It's interesting because day 1 and day 2, I was fighting them to let go of the handrails. They just could not walk without the handrails. And finally, on the 3rd day, I guess I scared them and they didn't use them. But it does seem like that subject was probably still a little uneasy about it. I don't know. And then, you know, I don't know exactly what subject I am. I'm in this data somewhere. But I wasn't an exemplary subject. I didn't use particularly less energy or get particularly more work than anyone else, even though I have a ton of training and I'm very comfortable on it. Compared to what? Yeah, I think I like somewhere around here. Yeah, sorry. Somewhere around here. This gets a little crazy, but.
One last question. Yes.
Did you measure like metabolic cost in the day 1 and day 2?
Yes.
So did that decrease your days?
Not consistently. There wasn't much change from day 1 to day 2. Or day 2 to day 3, actually. I'm sorry, I didn't hear. Oh, I see, in that particular subject. Yeah, I'm not sure. That's why I really made sure he didn't use them at all on the 3rd day. Because the 3rd day is the data we present the data.